what's online.
Well,
What are we, 241, 243, something like that?
Yeah, there's a couple of things where I've noticed changes, like in the yesterday, like the one in the beginning of the last session. I came in and was like, that's not what it says online, and it's like, and then I refreshed online. It's like, oh no, this one. It's like,
So his poster is showing.
depends on when you last loaded the page.
so I know what I'm. Oh yeah, I might. Yeah, maybe I should move forward.
Yeah, I was going to go to the corner. Well, maybe I'll set up there for the session.
Back, they have a printed out list and guys to help.
I've got the other person's laser pointers. Just quickly ask. Just one announcement. One of the audience members volunteered their laser pointer yesterday. Is he or she in the audience? I have it with me. No one? Okay. If you guys hear about someone who's missing a laser pointer, direct them to me. I've got the pointer.
That's the right one. Okay. So there's also some website where you can search for your poster. But are they at least close to each other? No, not really. Not all. Yeah.
Because I'm on in the last session. I'm on this afternoon. But I was thinking like this afternoon.
Same here. Yeah.
But I have my. Yeah, exactly. So I just. Can I take it? I think I'm sitting right next to it. Oh, so
Monday.
chat to you afterwards about.
Yeah. Okay. That's fine. That's good. We should. Yeah.
Okay, good morning, everyone. I think let's get started. Could we have the first slides up on the board? Okay, so welcome to the first session of the morning. Our session is titled Small Body Science Using LSST and Other Survey-like Data. And so this session will have, I think, 8 talks, of which the first one is an invited talk of 20 minutes, and the rest are 10 minutes. We're going to be really strict with the time, so invited talks will have 17 minutes for the talk and 3 minutes for questions, and the remaining talks will have 8 minutes for the talk and 2 minutes for questions. So our first talk is by Zalcho Ivizik, and he will be talking about the small body science possibilities with Rubin's LSST. Thank you.
Good morning, everyone. Thank you for inviting me. Am I close enough to microphone? Can you hear me in the back? Good. So I would like to give you a status update on where we are with Rubin construction and remind you about the huge data set that we will start producing in about a year. And some of the solar system discoveries may be happening in less than 2 months from now. We are still optimizing our commissioning schedule, but there is a possibility we could use commissioning camera to get some solar system discoveries. So I assume there would be some people at this meeting who are not very familiar with Rubin and LSST and our solar system program. So first half of my talk, I will go briefly through motivation for this project. And then I will the second half of the talk will be updates that I got from Mario Juric, who is head of solar system pipelines for Rubin. I'll show you where they stand and what to expect over next year. So the one thing that is different about Rubin Observatory compared to other 8 to 10 meter class telescopes is its field of view. That's the main difference that distinguishes Rubin Observatory, and that is the reason why we can scan the sky 100 times faster than any other large telescope. Here you can see Gemini South field of view in the upper right, and the bottom right is Rubin Observatory's field of view. It's 100 times larger, and that is important if you want to look at time domain, if you want to discover moving objects like asteroids. We will be using a filter set that is very similar to the SDSS filter set, except that SDSS Z band was split in 2. The one we still call Z, and the one further into near infrared is called Y. We will have 6 bands. There will be no time allocation committee. The observations will be scheduled using, if you will, AI code, the brains of the observatory, that has parameters for cost-benefit analysis, where your cost is time lost on observing and slewing, and your benefit is then obtained signal-to-noise ratio that depends on observing conditions, on background brightness, on where the moon is and what is the atmosphere doing that night, seeing, etc. This is all done in real time. Every 40 seconds, we need to make another decision where to observe and which filter to use. And over 10 years of LSST, it will be 2 million such decisions, 2 million images. Each one will be 3.2 gigapixels. Here is just an illustration, simulation of one observing night, sped up by factor of 1,000. So each jump of the dot corresponds to 40 seconds of real time. The lines show galactic plane, ecliptic plane, horizon, etc. Let me see if this will work. It didn't work, yeah. So it's I had the same slide in another talk yesterday, it didn't work. It's a video of our telescope moving. The point is that it's moving really, really fast. So it can slew from this direction to that direction in about 20 seconds or so. Typically, it's slew to next field 5 to 6 seconds. It's very, very fast telescope. The camera is pretty much done. It was shipped from laboratory in California, SLAC laboratory, where it was assembled and tested, to the summit in Chile in May of this year. This is one of the photographs where we were taking it from the crate to clean room at the summit. It's now being cooled down, and in a few weeks we should start the remainder of electro-optical testing, and it will go to the telescope in December of this year. Meanwhile, we will be using commissioning camera that looks from the outside just like this one, but inside, instead of 189 science CCDs, it has only 9 CCDs. But it's still powerful camera. It's corresponding pretty much in a tandu in the surveying power to dark energy camera on 4-meter telescope. So there will be some nice data sets, and I'll tell you later, we plan to commission solar system pipelines using commissioning camera. So again, to emphasize, the goal of an observatory is not just to produce those 2 million images, but also to process them so that they are calibrated astrometrically and photometrically. And then we will run pipelines that will recognize objects in these images, measure their properties, and publish them in regular data releases like many other surveys. On top of that, we will also have real-time processing, so-called alert pipeline, that will, within 60 seconds, ship the image from Chile to California, subtract that new image from the average of the old images, look for all objects in that difference image, match them to known object catalog from MPC, tell you if some object is known asteroid or not, and for other detections, it will attempt to fit orbits. So there are 3 classes of products. So for asteroid science, if you want to look for activity on asteroids or discover new ones, 60-second alert stream is interesting. But also if you are interested in statistical studies of asteroid populations, then data release will be also important, because it will be all the data we have processed with the same pipeline, calibrated with the same calibration input, and then all the best orbits will be available with very precisely defined selection functions. Here is an example of this alert production. So you subtract 2 images. If there is nothing, you get noise. In the second row, there is a new object, which could be an asteroid. It could be exploding star. And when you subtract 2 images, you can clearly see that there is a new object. And then you measure its position, its brightness. You ask, does it correspond to a known asteroid, etc. And then you put it together in a package, in an alert of a few kilobytes that you ship to everyone in the world within 60 seconds without any restrictions. Anyone can get to this data. Where do we stand with the construction? The top row is computer-generated images of the observatory telescope and the camera, probably 20 years old or so. And the bottom row are the photographs of the actual hardware that are less than a year old. So telescope looks like it was supposed to look like, telescope 2. And the camera, as I showed you, was just shipped to the summit. So the camera was tested, it works. This is pupil image of an old photograph of Vera Rubin, who the observatory is named after. And each CCD has 16 segments, 16 amplifiers to enable 2-second readout. So it is 3.2 gigapixel camera, but the readout time is only 2.4 seconds. That is needed to have a high observing efficiency. Out of those 3,024 amplifiers, only 3 are not operational, and the rest of them are, so the camera is in good shape. So these are the dates for the remainder of construction. We just shipped the camera to Chile. M2 secondary mirror was put on the telescope a week ago. This week we are putting commissioning camera on the telescope, and in a week or two we will integrate primary tertiary mirror with the telescope. So in a month from now we will have an operational telescope, and we will sometime in September start obtaining the first on-sky images with the system. Meanwhile, we are testing the big camera, the main camera. It will go to the telescope in December, and sometime in January or maybe February of next year, we will get full 3.2 gigapixel images with the big camera. It will take us few months to fine-tune the system. We also budget 2 months for science quality LSST-like surveying, and those 2 months of data will be used to demonstrate that we meet all the requirements, at which point the construction project is over and Rubin Observatory becomes one of the units of NOAR Lab, which is US National Observatory, and will be run jointly by NOAR Lab and by SLAC Laboratory in California. The first data release will be 1 year after LSST starts. LSST, we think, will start late next year, so in late 26, there will be first data release. However, the asteroid data will be produced from day one of LSST. Indeed, some will be produced in commissioning, and there is quite a high probability that we will be making some discoveries few months from now with commissioning camera. So what do we expect? Here is a typical simulated night. In one night, we will have detections of about 500,000 asteroids on average. To remind you, today we have orbits for about 1 million asteroids. In 3 years, LSST will discover another 5 million asteroids. So 3-4 years from now, there will be 6 million known asteroids. And then LSST will continue observing them for 10 years. So on average, after 10 years, there will be 300 observations of each of those 5-6 million asteroids. So we will have light curves, we will have precise colors for these asteroids. So today we have 1 million asteroids, but for most of them, we only have basic information that allowed us to fit orbits, but we don't have exquisite light curves. We don't have very accurate photometry, only maybe for a few tens of thousands. So this will be a different way of doing asteroid science based on big data. So what can be done by the project will be done by the project to make it more efficient for you to do solar system science. So this is our alert production loop with focus on solar system objects. So we will be connected to MPC. MPC will be an integral part of this framework. Every morning we will sync with MPC orbital database. We will compute ephemerides for that night. So whenever we find new object in different images, we will ask, is that consistent with a known object? Then we will report all the measurements and discoveries to MPC. And then I will not go into details, but every night we will get 2 observations of every point on the sky. We will have so-called tracklets. We will measure not just position of objects. We will effectively have little vectors. Because there are 2 observations, we will know where on the sky and in which direction a new object is moving. You may be familiar with HelioLink 3D, developed by Matt Holman from MPC and his group. We re-implemented that idea, that algorithm. We have operational pipeline. If you're not familiar with it, there is no way I can explain it in 1 minute, but you can look it up. There is a great paper written by the MPC team. That code, that algorithm, allow us to search for all possible orbits consistent with data, and these are hundreds of billions of possibilities. But because their algorithm moved us from old algorithms that scaled with n cubed, when n is number of possibilities, to n log n, we are now golden. Now we can do it with normal available computers. It's not science fiction anymore. Essentially, we tried every possible orbit, and we get the best fitting one. So where do we stand with this? This is a slide from Mario Juric. I would have used bigger font. So there are a bunch of components of our pipelines. And the message here is they are either done or we know quite well what to do and how to do it. The main piece that is missing is actual commissioning of these pipelines on real data. We have done lots of tests based on simulated data, but we have not done it with real data. And when you start playing with real data, then you discover that there is always something you didn't think of when you did simulations. We do have a little bit of testing on real data. So Ari Heinze, who used to work for PainStars and Atlas, he's now part of Rubin team in Seattle. He used Atlas data to discover new asteroids that were not discovered before because algorithm was not as good as this new algorithm. So old data, new algorithm, new discoveries. Here is another example of PHA discovery that Ari did that the old algorithm didn't pick up, but it's now regular. It's not special in any way. Algorithm will pick it up. Here is yet another example based on ZTF data. So we are running recovery code on ZTF data and testing how well it works. And now we are trying to implement commissioning strategy that will use commissioning data. And we are still going back and forth thinking how it will look with respect to other science cases. We have 4 main science themes that we are trying to address with Rubin and LSST data. Solar system, of course, is one of them. But now if we start producing science with solar system, if we release early during commissioning this data, what will other people say who are not interested in solar system but other discoveries? So there is some astropolitics there. We also will have our first light, or what we call first look celebration press conference. We want to do something bombastic like JWST did. But because of that, we also need to be careful about releasing data prior to that usually embargoed press release. So we are still thinking through how exactly to do commissioning, but it's highly likely you will start seeing asteroids discovered by Rubin in a few months. This is example, again, of commissioning using our calibration telescope that we call auxiliary telescope. So that basically tests all the software pipelines we have, as well as software for transferring data from Chile to California, and of course, automatically triggering pipelines and all the processing, it's working. I was told I only have 2 minutes, so I will not read every single word. But the main conclusions are on my last slide. So we are in good shape with solar system pipeline. The team is not very large, but it is very good. There are 4 or 5 people working with Mario and Ari. It is integrated with MPC. There is very close collaboration between Rubin Solar System Pipeline Group and the Minor Planet Center. We are just about to start commissioning. We know, based on other similar surveys, that commissioning always brings up new problems. We think we will be able to handle most of them, but it's almost certain that there will be some last-minute changes to our schemas, to our software, to what we can give you and cannot give you. So for you, it would be good to start early using whatever you can get either through MPC or directly through alert brokers. And then you also modify your pipelines if you want to jump on early science. And as I said, most of those 5 million objects will be discovered during the first 3 years of LSST. So if you want to be there when the cake is cut and do some great science, you have to start preparing now. Not when the data start flowing, but now. And you still have a few months left. So thank you very much.
Any questions?
Hi, Andy Rifkin, Applied Physics Laboratory. Great talk, really looking forward to Rubin. 2 related questions. 3 million asteroids is obviously a lot. 5 million. Oh,
What's 2 million asterisks?
That's 60% more, isn't it? Or even more than that. So can you translate that into like a completeness size for the main belt?
Right. So 50% completeness for main belt will be a few hundred meters, 200 or 300 meters, depends whether it's C-type, S-type, etc. But it's in hundreds of meters. Very detailed information indeed is available in our science overview paper, in several solar system focused papers by Jones et al. There are several conference proceedings by Juric et al. All these numbers exist and they're easy to find. And you can send me email later, I'll send you links.
Great, well then I'm still gonna ask my second one, which is, of course 140 meters is the number that people are thinking about for NEOs, but smaller sizes have also been interesting for, in the US Decadal Survey. So at 50 meters, do you have any kind of idea of that number? I haven't seen of what your completeness might be at 50 meters for NEOs.
It's few tenths of percent. Maybe it's 20, maybe 40, I forget. What I do remember is that for the NASA mandate of 140 meters, conservative estimate is between 65 and 70% for PHA. We think that we might even go over 80%. It's asymptotic, so I doubt we'll hit 90%, but that's a man-made number. So I think we'll get very close to finding most of 140 meters and larger. Again, there is curve, beautiful, beautiful curve, as someone would say from the US.
There's another question from online.
One online question from Melissa Brooker. I thought we had to wait for the sky templates to get solar system data.
Correct. A very good point. We will not have the entire sky covered with templates when we begin LSST. Templates are these average images, at least 3 to 5, roughly speaking, that you use to subtract new image from. And so for each position on the sky, you need to get at least 3, but optimally 5 observations. To do that, you would need a full year, because I'm sure you know Earth goes around Sun, and you can't see everything. So it will take us at least 7 to 8 months to have access to the entire sky. So on day 1 of LSST, we will not have templates for the whole sky. But we will not wait for the data release 1 to start doing that. As soon as on some area on the sky, we have enough observations to make template, we'll trigger software to make template. Next time we observe it, we will ask with new image, is there a template there? If there is template, subtract the report. So first year, it will be gradual increase in the coverage of the sky. After data release 1, the entire sky, those half the sky we will observe will be covered, and then every observation will have alert stream reported.
Hi, Dennis Bolowitz. How many nights would you need to determine whether an object is interstellar or not? So to have a precise enough measurement of the eccentricity.
Interstellar, you say? Mm-hmm. I'm not sure how many nights, but I believe that already with 6 detections, it should be possible to have a good posterior. Now, typically that will happen on average maybe in 8-9 days. Or if you ask what is the return time to a given point on the sky, then on average it's about 4 to 5. It's modulated by seasons and so on, but it's like about 10 days. And there are already people developing pipelines that will be focused particularly on that question, what is my Bayesian prior for these observations that this is not solar system object, but interstellar object.
Hi, Jelko, here.
Hey.
Hey, all right. Thanks, great talk. So I was wondering, so I understand that you have integrated into your pipeline, like a piece of the pipeline that's going to send all the asteroids to MPC, right? But at the same time, those alerts are going to the brokers, right? So my question is, when you send the alerts to the broker, will they have like a flag or a probability of being an asteroid, or they're going to go like any other alert?
They will have information if they are already in MPC's catalog downloaded that morning. So if there were known asteroids 24 hours in advance of observation, alert will have a flag that says this is matched to known asteroid, and the probability is very steep function of distance, so it will be 0 or 1 in the first order.
And if it's an unknown asteroid?
If it's not known asteroid, then you will not know at that time. Later, MPC will have information that after we got additional observation, it was a new discovery. But alerts, once they are issued, they are like etched in stone, and they don't change. It's in a database. There will be another database that will be updated. But alerts, once they go out, they are frozen.
Okay, thanks.
Okay, let's thank the speaker again.
Thank you.
Okay, our next talk is a virtual talk online, and that's by Jean-Luc Margot. And he will be talking about a large data set of asteroid rotation periods.
Thank you, hello everyone. Can you hear me?
Yes, we hear you.
I'm pleased to be able to present UCLA undergraduate Adrian Lam's work on the determination of a very large number of asteroid rotation periods from the WISE dataset. Now, asteroid rotation periods are important for a variety of reasons. And the first one is that their distribution tells us about the internal structure of asteroids. We've noticed that there's a spin barrier for all objects larger than about 200 meters at a rotation rate of about 2.2 hours. And that tells us that large asteroids are mostly rubble pile and are not held with strong cohesive strength. These spin periods also inform us about the formation of binary systems, which are quite prevalent among asteroids, and about the formation of asteroid pairs, and so on and so forth. There's an important use in the shape modeling context when we're trying to reconstruct the three-dimensional shape of an asteroid on the basis of radar images or optical images. It is really crucially important to have a good estimate or even a few trial estimates of the spin period. And that is true also in the case of thermal modeling, where the flux might vary as a function of rotational phase. The traditional approach to obtaining these spin periods is to do light curve photometry. And for a typical object, you'll notice that we have a double-peaked asteroid light curve for a single rotation of the object. And this is easily done when you have a long time span or finely sampled observation sample. However, in the case of large surveys, sometimes what you get is sparse data or time-limited data, and these present additional challenges, and this is what we're addressing in this talk. There's huge potential, as you've heard in the previous talk, because large surveys are currently delivering or will deliver data for millions of asteroids. And currently already there are data for hundreds of thousands to 1 million asteroids. We're using the WISE photometry, although we're using a carefully curated data set of the WISE photometry. So we're using the Mervold et al. Data set in which some problems with the data have been eliminated, in particular cases where a background source was attributed to an asteroid or vice versa, cases where asteroids were close to one another and the flux of one was attributed to the incorrect asteroid, and also cases where there were large ephemeris discrepancies between the predicted position and the reported position of the object. And we're also using the flux uncertainties of Lam et al., which are larger than the published flux uncertainties for WISE, and that paper describes why those are the correct uncertainties to use. The WISE dataset has a very specific cadence due to the orbital geometry and data taking cadence. So we'll find that most time differences between images are either 1.6 hours or 3.2 hours. And as a result of this very specific cadence, we do expect aliasing, and there are mirror frequencies at about 3.8 rotations per day and 7.6 rotations per day. But we're going to actually turn what is typically a disadvantage into a strength, and we're going to use the fact that these mirror frequencies are very precisely known to allow us to determine additional rotation periods. So Adrian has published about 4,000 asteroids in a previous work, and in this work, he's observing a much larger data set, about 20 times larger. Here's a schematic of our data processing pipeline. We use the W3 and W4 band of the WISE data set, we require at least 12 observations that have a minimum flux variation of about 0.3 magnitudes, and also a flux variation that is substantial compared to the flux uncertainties. And once we've identified those objects, we apply a conventional second order Fourier series model, and we compute the chi-square parallelogram at a variety of trial spin periods. We then reject a number of anomalous solutions, either long period solutions that are much larger than the span of the input data. Low signal to noise ratio solutions are rejected. Solutions with anomalously large amplitudes, much larger than the input flux variations, are also discarded. And solutions with large period uncertainties are also discarded. How do we know how well we're doing? We're using a control set based on the asteroid light curve database. There are about 2,000 light curve solutions in that data set with a good quality code, and these form the basis of our comparison data set. We consider that we've identified the correct solution when the relative error between this reference solution from the light curve database and our solution is less than 5% in terms of relative error. So here they are, those 2,000 solutions, or best fit frequency on the horizontal axis and the light curve database frequency on the vertical axis for this overlapping data set. And what we find is that in most cases, we recover the reference solution with a 5% relative error. And these cases might look something like that. Here's a sample variation as a function of time in the top plot, and the folded light curve in the bottom plot, where we see that we've recovered the reference solution published in the light curve database. Now, as I mentioned, we're going to use the fact that there's these mirror solutions to identify further spin periods. So we're computing the mirror solution at those two mirror frequencies to find that there's an additional third of our data set that provides the accurate solution. So the secondary and tertiary solutions add about 34% of asteroids with a correctly identified spin period using, again, this aliasing property. And then finally, in about 14% of the cases, the solution is inaccurate, although you can see near the bottom that many of these do appear to be actually fairly close to the correct solution. So to summarize, in about 86% of the cases, one of the three candidate periods matches the reference with less than 5% error. So we've derived spin periods for about 21,000 asteroids. Most of these do not have any light curve database entry at all. 81% of these periods are completely new. We present three candidate period solutions for each light curve. And again, if you're in a shape modeling situation, this is a game changer. You can use all three of them, quickly identify which one is the correct one, and proceed with your shape modeling work. One of the three is accurate in 86% of the cases. So this yields a substantial increase in the number of asteroid spin periods. We can use these data to discover or confirm unusual or unique objects. They can greatly facilitate shape and thermal modeling work. And we can also use this technique and this data set to enable a joint analysis with other ground-based sparse surveys. Thank you for your attention.
Thank you very much, especially for staying in time on the second. Questions, yeah.
Hello, yes, thank you for your talk. Dmitry Vavila from Paris Observatory. So I have chances to work with test data, and soon we will have a paper published about this our periods for the test data. And in this paper, we show that sometimes the second order of the Fourier series is actually not enough to find the period. So basically, like the second order gives you one period, but if you go to the third or the fourth one, so you will find the true one, basically. So I would like to you to maybe to read our paper. It's accepted and will be published soon, and maybe consider implementing this also in your work. I think it will be.
Thank you. Yeah, this is a great point. Please send me a link to your paper. It may account for some of these inaccurate solutions that we have.
We have next online question.
Yes, we have one online question from Javier. Is the method and the LSST cadence effective in measuring ultra-fast minute periods with your method?
No, unfortunately, we're unable to measure ultra-fast rotation periods, primarily due to this cadence of, at least with the WISE data, the minimum cadence is something like 1.6 hours. And so we cannot measure very fast rotation periods, unfortunately.
Okay. Gerbsbauer, University of Maryland. Nice work, Jean-Luc. I'm wondering, have you found much of offset between those? Do you have a subset of objects that have had two epochs or two visits? And have you found offsets between, in your period solution between those two epochs?
Oh, I think I see what you're saying. The WISE observations are such that typically you have a cluster of observations, and then occasionally a few months later you have similar observations. Right. A different cluster. I actually do not know the answer to this question, but I'm sure that is something that Adrian has looked into. I think we're publishing both solutions. So when there's separate clusters, we publish two separate solutions, and it would be indeed very good to see if they're consistent with one another or not. I will follow up with Adrian on that.
Thank you.
Okay, thanks, Jean-Luc. Let's thank the speaker again. Okay, our next presentation is by Andy Rifkin, and he's going to be telling us about diversity of spectra in asteroids.
All right, thank you very much. It's like, whoops, I already went one too fast. All right, thanks for coming. It's a pleasure to be here in South Africa, where it's winter. Back in North America, it is brat summer. So I'm happy to be taking part in that as well. So I'm going to be talking about low albedo asteroids here. There are, at the very top level, there's two kinds of asteroids. If people who are not asteroid people this might be the, how they think about it. They're the high albedo bright ones, which are typically associated with rocky or metallic compositions. Typically, they don't have a lot of water or hydrated minerals associated with them. And then there are the darker ones, which are associated with ice and organics. That latter group includes Bennu and Ryugu and Ceres, which are not on this figure for various reasons. Emily Lakdawala made this great figure several years ago. And one of the reasons that we care so much about low albedo asteroids in particular is that there's geochemical evidence that the higher albedo and lower albedo material formed in different parts of the solar system. If you look at the isotopic evidence, there is a group called non-carbonaceous, which are the ordinary chondrites and others. There's the carbonaceous group. Isotopically, again, there's this evidence that they formed in different parts of the solar system. It's been interpreted that Jupiter kind of was between those two groups, and then the carbonaceous stuff came in later on to the asteroid belt. And there's been dynamical models as to how that happened, most notably the Nice model and the Grand TAC. So for the higher albedo group, we can look in the near IR and figure out what kind of their silicate compositions are. The low albedo objects don't have so many absorption bands in those near IR kind of 0.5, I guess is visible, out to 2.5 microns. You don't get a lot of different things going on in the low albedo asteroids, so you have to look at slightly longer wavelengths. The 3 micron region in particular has absorptions due to OH and CH and NH, and this is where you would make measurements of hydrated or hydroxylated or organic materials in general. At least that's where the deeper bands are. So it's somewhat easier, except for the Earth's atmosphere. So the Earth's atmosphere also has water in it, at least in lots of parts of the world. So that makes it a bit harder to do from the ground. Nevertheless, we can see a variety of band shapes. So basically, the question we're faced with in a lot of ways, this is shown in this spectrum of Bennu from OSIRIS-REx. The taxonomy that we hear about when we hear about B asteroids or X asteroids or whatever comes from that left part. But for low albedo asteroids, most of the mineral identifications that we're doing come from that right part, and they don't overlap. Plus, again, this box region shows that the region you can't get from the ground. Nevertheless, we persist. So there are a variety of band shapes that we see in this region. These are all asteroids. This is a paper from a few years ago, but the data is somewhat older. There is this group that we see that looks like Pallas, so that looks like the carbonaceous chondrite meteorites, the CM meteorites in particular. We could say you get this kind of linear band coming out of that blank region due to the atmosphere. We think that's phyllosilicates. And then there are these others down here, including Ceres, and they have additional features that we think are due to ammoniated minerals. There may be ice or ice frost. There's also phyllosilicates there. And we don't see these spectra in the meteorites, which is an interesting question. So basically, these large asteroids, we can say, what do the small asteroids look like? Because these are all hundreds of kilometers in size. So we started this program years ago. It's a survey. It was kind of a I don't want to say an accidental survey exactly, but it kind of built up over time. Using the IRTF, using the SPECS instrument, both before its upgrade and after its upgrade. And so we published the results in various papers that came out around the time of the pandemic and through when the pandemic started. So basically this in the end had 150 low albedo objects in it. And for our purposes here, although we're going to be a lumper, I'm going to be a lumper. I don't know what you guys are going to do. And just kind of put all of the different groups of asteroid spectra into two different groups. Is the band minimum to the left of that vertical line at 3 microns or to the right? And for the rest of this talk and in this paper, we called the ones on the left sharp types, following Dries de Keer's terminology, and on the right is not sharp types. And that's the division we make. So again, the sharp types look like the CM meteorites. They look like a lot of asteroids. Bennu looks like this, Ryugu looks like this. The NSTs are Ceres and Themis, and I don't think we've visited any objects that look like that yet. And what we find is that both STs and NSTs are found in every taxonomic group we look at, except for the CH asteroids specifically. So the B asteroids have both STs and NSTs. The X asteroids have STs and NSTs. This histogram is of the wavelength of the band center and number, and the color scheme there are the different taxonomic groups, which again are defined based on the shorter wavelengths. And it looks like there's even a hiatus between them at, looks like there's one clump shortward of 3 and one clump longward of 3, which is not a circular argument. It needn't have been that there was a division there just because we put that line there. We can look at the largest objects again, even though I said we were going to look at the smaller ones. This is part of it. We have data for all 50 of the largest main belt asteroids, and they divide pretty evenly into the STs and the NSTs. And that's 2 minutes until the end of the slot, or 2 minutes until end of the slot. All right, so we're going to fly through this. Basically, the NSTs, even though we don't see them in meteorites, are a large fraction of what's out there in the main belt. We can look at their statistically how those groups differ, again, only defining them based on where that band center falls. And we see that the large and the small NSTs tend to be farther out in the solar system than the STs. You know, in their semi-major axis. While large and small objects of the STs don't differ from one another, and large and small NSTs don't really differ from one another. I'm just going to also note that the NSTs look spectrally like comets, at least at the top level. So in conclusion, and again, I know I had too much to talk about here, a sample of 150 low albedo objects show that there's at least two groups of spectra based on their 3 micron band shapes. The two groups are about equal in number, at least at the largest sizes, and that the NST group that we don't see in the meteorites is not an insignificant group. So we're of course going to keep looking, but I see my time is just about out, so I will stop there. Thank you for your time.
Thank you very much. Questions?
Thanks, Andy. Do you know if there's a difference between the spectral effects for surface grain size in this? Can this have differences as well as composition at that kind of wavelength range?
I don't think it's going to be a grain size thing. We have, I guess I did say we haven't had a spacecraft at any of these, but I guess that's not true. We have had a spacecraft at Ceres, and Ceres is pretty homogeneous everywhere except for where they see, you know, specifically like ice or carbonate. So I don't think it's a grain size thing. We need to look at family members to see how spectra, you know, a lot of these are family members, are family parent bodies, and we don't have the data to look at smaller members to compare. Hopefully we'll be able to do that with JWST, but we'll see.
The wavelength range you were showing is almost identical to the wavelength range of the SphereX mission. And they will have predictions are thousands of objects. Are you excited about it? Do you think that it will be possible to do analysis like you presented with those thousands of objects from SphereX?
I'll cherry pick your questions. I am excited about any space telescope that wants to look at asteroids. Gerbs and I have talked about SphereX a bit, and because we've been doing the conference tour together, and he's been talking about SphereX. So hopefully we'll be able to use that in that sort of way that you discussed and pull some things out. And I know Casey Liss has had abstracts about that. So yeah, that'd be great.
One more question, if there is one. If not, then we thank the speaker again.
Okay, next up we have Hee-Jae Lee, and he will be telling us about asteroid shapes derived from KMTNet and Gaia data.
Hi, thank you for the introduction. Hi, I'm Hee-Jae Lee from the KASI. In this presentation, I would like to talk about the shape modeling of asteroids with KMTNet and Gaia dataset. The shape model and spin state of asteroids are regarded as one of the most important physical properties for understanding their nature. These physical properties are provide the fundamental information for understanding their other physical property. And also the shape and spin of asteroid offers the important clue for investigating each dynamical evolutionary process. Then, how can we investigate the shape and spin of asteroid? One way to resolve the shape and spin of asteroid is to study each time series photometric data. When we conduct the photometric observation of an asteroid, its brightness is changing due to its irregular shape and rotational property. So the light curve of asteroid provide information about the shape and spin state of asteroid. Furthermore, the asteroid light curve can be divided into two types. One is the dense light curve, and the other one is the sparse light curve. dense light curve is more classical type light curve, and these time light curve are obtained by the targeting observation for a single asteroid and observing it intensively over a single light. And in construct, a sparse light curve has very long interval between each observation point. And it usually obtained from the all-sky light curves, all-sky survey such as Gaia or Atlas. And each type of asteroid, the light curve has very clear advantage and disadvantage. Generally, dense light curve has the advantage that the rotation period can be detected directly from the light curve data. This allows us to find a solution very quickly based on the known rotation period. However, with sparse light curve, it is impossible to find the rotation period directly from the data. So this makes it more time-consuming to find the solution. Nevertheless, the sparse light curve data remains extremely important for studying asteroid shape and spin state. Because dense light curve requires intensive and targeted observation, making it difficult to obtain the data for investigating shape and spin state. On the other hand, sparse light curve are relatively easier to obtain the data due to the abundance of public available data from the whole sky survey. So this advantage, the advantage and disadvantage of both types of light curve lead to wonder which type of data would be best for efficiently studying the shape and rotation of asteroid. And we thought that combining the both type of light curve might be the solution. So we decided to test it. In this study, we used dense light curve from the KMT-net and sparse light curve from the Gaia telescope. KMT-net consists of three 1.6 meter wide field optical telescope, and the telescope of this network are spread over three different stations at similar latitude in southern hemisphere. Hence, this network system enables 24-hour continuous monitoring of the same object. This wide field and round-the-clock observation of KMT-net provide the ideal condition to obtain dense light curve. Therefore, KMT-net observed the dense light curve over 30,000 asteroids every year. And the Gaia Space Telescope has been conducting all-sky survey since 2014. The observed data is being released gradually, and this study using the Gaia DR3. Gaia DR3 includes sparse light curve data for a total of about 160,000 asteroids. From now on, I will show you how effective it was to combine and analyze the two types of asteroid light curve. First, we searched the asteroid with data from both KMT-net and Gaia DR3, and we found that a total of 40,000 asteroids were observed by both facilities. Among these, 750 asteroids had a shape model construct using only sparse light curve. I will now present the result for target where the shape model can be detected using only sparse light curve and demonstrate how the additional of dense light curve impact this result. 2000 EB133 is an asteroid for which a unique solution was determined using only Gaia data. This figure shows the shown here represent the rotation period analysis using shame model only Gaia data set. Even if we using only Gaia data set, we can compound the rotation period here. Next, we combine this with the dense light curve observed by KMTnet and performed an analysis. We can show it's shown that the rotation period can be more clearly comparing to when we use only Gaia data. And additionally, we obtain the rotation period is approximate to 16 hours. It is very well matched with the rotation period obtained from dense light curve. And this is the comparing the shape model and rotation period of this asteroid. We can see that both results were matched. The second case is for target where a shape model could not be obtained using Gaia data alone. We can see the sparse data alone did not provide any rotational period. However, when we include the dense light curve from the KMTnet, we are able to determine the rotation period shown here. Based on our analysis, the obtained rotation period is about 14 hours, which very well matched, also very well matched with the rotation period obtained from dense light curve. And the shape and rotation parameter at this time here. Yeah. So we successfully implement asteroid shape model by combining Gaia's sparse light curve and KMTnet dense light curve. For this result, we are able to determine two key points. First, the rotation period detected from the dense light curve very well matched the final period obtained from shape modeling. This improves efficiency by narrowing the range of period we need to search. Second, using only sparse data did not provide unique solution for the asteroid. However, by cooperating with the dense light curve, we are able to identify the solution. Therefore, based on this find, we plan to analyze a whole interior data set, and also we plan to conduct the statistical study on asteroid spin parameter. This is the end of my presentation. Thank you for your attention.
Thank you. Because we are a bit short of time, one short question. And perhaps afterwards.
Yeah.
Thank you again.
Thank you. Oh.
EJ, this is great work. I'm wondering, are you thinking of folding in other data sets to complement the KMTnet besides Gaia alone?
Sorry?
Are you thinking of exploring adding other data sets to the KMTnet?
Yeah.
In addition to Gaia to converge on your periods more?
Yeah.
Well, yeah. There's a lot of archive now. Archive data. Yes.
Yes, right. Yes, we downloaded the archive.
For instance, Atlas. Atlas is a good example.
Yeah.
Okay, our next speaker is Tobekile Ngwane, and she'll be showcasing the Rapid NEO follow-up program that has been initiated at the South African Astronomical Observatory.
Good morning, everyone. My name is Tobekile. I'm a second-year master's student at the University of Cape Town, and today I'll be presenting my MSc thesis that focuses on the rapid follow-up of near-Earth asteroids. So near-Earth asteroids are asteroids whose orbits bring them close to Earth. And so far, there have been 35,000 NEAs that have been discovered. So if you look at the discovery statistics animation below, it shows the number of asteroids versus the absolute magnitude. And you can see that over the years, the median size has been shrinking. And if we jump to 2023, you can see that 61% of the total discoveries for that year were less than 50 meters in size, and the median size for that year was 37 meters. So small NEAs can still cause significant damage, as shown by the 18-meter Chelyabinsk meteorite in 2013, and that is why continued research and observations of the small NEA population is important. And particularly, rapid follow-up of small NEAs is important because when they come close to Earth, they're bright for a little while, and then they fade away quickly. So we only have a small window of opportunity to do our follow-up observations. So this project aims to enhance the rapid follow-up observation capabilities of NEAs using the LISETI telescope, and that is the program I'll talk about today. So for our observations, we use the LISETI telescope, which is a fully automated and robotic 1-meter telescope, and we use the McCordy instrument on that to collect images in G, R, and I, and we also collect unfiltered images. So we have an automated Python script that checks JPL Scout every 15 minutes, and it looks for observable targets, and if it finds any that are observable for that night, it will automatically send an observing request to SAO's observatory control system. So it detects these discoveries and sends an automated observing request, and we have a 10-minute observation cycle that runs through G, R, and I, and we have that interspaced with clear images. So these observations are scheduled in robotic mode, and then we have systems in place that will continuously retrieve the latest schedule and then inform the PIs, which is me, when the observations are ready. So all of this is done without any human intervention. So for our unfiltered images, I manually measure the astrometry. That means me selecting the asteroid through each frame, and then we submit that to the Minor Planet Center, and this helps us contribute to the orbit refinement of these newly discovered NEAs. So for the remaining images that we took in the G, R, and I filters, we run that through a photometry pipeline, and that usually happens a few days after because the pipeline only works with asteroids that have already been designated. So from there, we compute the G, R, and I, we get the calibrated G, R, and I photometry, and then we compute the color indices from that, which is G minus R and R minus I. So a majority of our observations have been done within 1 day of discovery. And if you look at the first plot here, that shows the number of asteroids versus the asteroid size, you can see that more than 3/4 of our observations were more than three quarters of our asteroids were less than 100 meters in size, which was our first goal to probe the small NEA population. And if you look at the second plot here, which shows the number of asteroids and the time difference between the discoverer's last observation and our first follow-up, and you see that more than 60% were done in less than a day, with 10% done within 3 hours. And this was our second goal, rapid response. So a faster response time would be possible, but we are limited by the reporting of these discoveries to the MPC. So if you look below here, I show an excerpt from the Minor Planet Center, and this is for asteroid 2023 QN7. And the first date here is the last observation for the discoverer, which is M22, and the next date is our first follow-up observation. And if you calculate that, we did this observation in 57 minutes. And that's because the Atlas node is located in Sutherland 2. Cool. Okay, So using those color indices that we calculated, G minus R and R minus I, we use that to determine the likely taxonomic type. So what we do is we superimpose our points on this decision surface that was generated by a trained machine learning algorithm by a former student. And this uses the Bastinian classification scheme to separate the asteroids into the different boundaries. So here I show 40 of our asteroids that we've managed to get color out of, and this is only a quarter of the observations that we've done. And the reason being is, these are the only asteroids that had enough SNR to give us reliable colors. So when we determine the likely taxonomic type, we don't only consider where it falls, but we also consider the uncertainty in its position. So we do that by using the Monte Carlo approach, where we generate 10,000 random pseudocolors around the asteroid and within the uncertainties, and we classify each of those individual points, and we tally that up and get a percentage probability. Okay, so if the taxonomic probability is more than 50% in a specific class, we give it that classification. For example, 2023 PR had 98% in the S region, so its likely taxonomic type is an S type. And for the asteroid that does not meet this threshold, we leave that as unclassified. An example is 2023 QW. So to conclude this, we've successfully implemented a rapid follow-up program. We've observed approximately 194 asteroids, and more than 3/4 of them were less than 100 meters in size. More than 60% were same-night observations, with 10% being done in 3. And our determined taxonomic distribution of these asteroids, it somewhat agrees with previous work, just that we observed a slightly higher percentage of S types, of the stony types, if we look at the S, consider the S and V. And one reason for this is because one possible reason is that we observed a different population size, and this could indicate a taxonomic distribution dependency on population size. So in future, we aim to automate this whole process, the astrometric measurements process, and expand to more telescopes like SALT. Thank you.
Questions?
Thank you for a nice talk. Could you maybe explain a bit better how you are scheduling the objects, especially with now an uprising number of asteroids there? How do you select exactly which one to use and when in the night?
So on JPL Scout, you can check the positional uncertainty of the asteroid, and if that's within the telescope's limits, it will select that asteroid and send the observation. So we check a lot of things, parameters like where it is in the sky and all of that. Yeah.
Hi, thank you
Hello.
for your presentation. I'm Miri from the Adam Mickiewicz University. As far as I understood, the algorithm that you are using for the taxonomic classification is similar to the fuzzy C-means. Have you tried that algorithm, or do you know it?
No.
Maybe it's a good idea to run it. It's also in scikit-learn package in Python, and then you can compare the results.
Okay, thank you.
Other questions?
Hi, it looks to me that, well, from your slides, which showed the 2 images of asteroids, it looks to me that your telescope is not tracking the targets non-sidereally, right? Is it possible to track objects based on their ephemeris motion?
I think it is non-sidereal tracking. Yeah, it is possible.
Thank you for the talk.
Thank you.
Okay, our next speaker is Marcello Fuccinoni, and he will be talking about BVI photometry to characterize NEAs.
So, good morning. I'm trying to give you an idea how it is possible to find groups of different asteroids using only 3 or 2 colors. And I was using a data set collected by literature of V minus V, V minus R, and V minus I colors for 475 asteroids. Here are the reference, and 577 colors deduced by the spectra with this formula. Okay. Sorry. So we have 4 data set, 812 asteroids with 3 colors, and the couple of other colors are here. Sorry. So we use 3 methods for analyze this data set. The 812 asteroids were analyzed with a multivariable statistical method, the G mode, which is published in Icarus by Barucci et al. 1987. And here is the results of our analysis. Here you have the group that was found by the method, which is able to analyze the set of objects with all the variables. Here in this case are only 3. And so we have 7 groups with the 80% of the total asteroids are unclassified, are outliers. And in these 7 groups, you have here the values of the average for each of the color, and the method allow us to have each asteroid located in one of the groups. The second method has been a decomposition of the of each distribution of each color with a linear combination of Gaussian curves in order to find if it's a single distribution or is a superposition of several distributions. This is the results for the 3 colors, and you have the 6 groups for each distribution are found to give the best fit of the general distribution. And here I have for 6 groups, the values of the colors, the peak of the values of the colors for the peak of each grouping Gaussian. The last method is a method that the authors called fast search and find density peaks, in which the method allowed to group the asteroid according to a defined distance in the space of the colors. And the way in which is working is find the cluster center defined as local density maxima located far away from each other maxima. So the method allowed to give to each of these clusters all the asteroids. Here you find in the space distance density. In colors, they are the center of the clusters. The center of the clusters are those asteroids which are well out of the total amount of the asteroid examined. On the other side, you have the core, the number of asteroids in the core, and the asteroids which are attributed to each cluster. This is the results. Colors represents clusters, and this is the results on the in the three colors space, and you see that is enough good the separation between a cluster is very good, is good enough, and we did also for each of the two colors data set, and we have the same results, 7 groups, and are clearly well defined the region of the color plan where the asteroids of different group fall. So, in conclusion, the information provided the three colors allow always to recognize a number of different groups of asteroids depending on the used method. The composition of color distribution with a linear combination of Gaussians is good, gave 6 groups, but it's not so easy to attribute each asteroid as a group because we are, of course, analyzing only one variable per time. And the G mode give a very well-defined groups, 7, with a cluster a confidence level for each cluster, which is of the order of 85–90% here. And also the last method, the rapid search and density peak, provide a very good classification for each asteroid 1. So to have an hint, so I have some hindsight of the kind of the meaning of each of these groups, it is possible to make comparison, statistical comparison with the average of the found groups and the average colors for the classification to which we want to make a comparison. Here you have, for an example, the values of the colors calculated by for the Baz-DeMeo classification taxonomy. Thank you.
Thank you very much. Questions? Thank the speaker. No.
Hi, Amanda Sikafus from the Planetary Science Institute. You said you ran this on a sample of, I think it was something like 850 asteroids. Do you have plans to run it on other samples or what's coming in from LSST?
This is what I was able to find in literature for exactly 475 in which we have an observation of colors. I showed the origin, and I found also large survey done with the spectra. And from the spectra, I calculated the colors, just to have a larger statistical sample. Yes, if waiting for LSST, I hope to have millions of data. Thank you.
Thank you.
Okay, our next speaker is Xavier Inocencio. Did I pronounce that correctly? And he will be talking about some of Earth's mini-moons.
We're just saying let's do just a little bit back. Yeah. Make sure they can hear you. This is your pointer, that button. Okay. Hello, everybody. My name is Xavier Inocencio. I'm a first-year grad student at the Florida Space Institute, joined with co-authors contributing to this project. And we're here to talk about the characterization of 19 IAU and using that as a proxy to learn more about the Earth mini-moon 2022 NX1. So what exactly is an Earth mini-moon? These are small bodies that are temporarily captured and orbit around the Earth similar to the way that our moon does. And they can be extremely hard to observe due to how irregular their orbits can be and how unpredictable it can be, their small size, and just add on to it, they're typically faint. And from a paper by De La Fuente et al. 2023, their population in terms of surface composition can have wide variety, and they can be as small as a few meters, which is important for us to do characterization of them. So going back to kind of the two things I mentioned in title slide, 2022 NX1 and 1990 UQ, from the left side is our Earth mini-moon that we want to know more about. And what we need to know is its albedo, and the only way to know that is by finding an object that has similar polarimetry properties to it. So we obtained VLT polarimetric data, and it indicated to be similar to 1990 UQ, which is a NIA and a potentially hazardous one. And for this work, we need to do light curve inversion and radar modeling to obtain a reliable albedo and comprehensive shape model of the object. And we obtained radar data from Goldstone observations in 2021. So just going into kind of giving the just cause of why we're doing this, this is a phase polarization curve for 1990Q in which both of them were about the same phase angle of 63 degrees. For UQ, it's at 3.2% for its linear degree of polarization, while 2022 NX1 is at 3.1 with uncertainties ranging about 0.2 to 0.3%, kind of covering that gap, allowing us to use the relationship of albedo and polarization to learn more about the Earth mini-moon. So going to the work that's been done so far in this research, this is from one of the TRAPPIST telescopes. We first started with observations that we got from there, and over on the right side is just tracking it over each frame, and we analyzed that to do the light curve, photometry, not polarimetry. From there, we kind of gather our light curves from observations, taking data from the light curve database, the TRAPPIST observations from north to south, and observations that were given from us from the Geneva and Danish telescopes by the respective observers. And from here, they kind of range from continuous nights to maybe a little bit more sporadic. But nonetheless, I might not be dealing with millions of light curves, but we have roughly about 32, which is good enough for what we need to do. So continuing, we're doing a period search to kind of find the best period. And there's been observers that have taken their own data to find their period. So we kind of use that to kind of tighten the constraint to find what exactly our best period result would be. And by measuring the chi-squared to the period, gave us a result of about 6.657, which is in line with the most recent published result for UQ by Warner et al. In 2021, which had roughly about the same thing. Once again, even though they may be similar results, it may not be unique, but it's still giving us confidence that we're doing this right and that UQ is a well-constrained object. Continuing on from the output of our period search, we're going to do a pole search to figure out the pole orientation of UQ, in which the graph on the right kind of displays that the best pole points in the pole orientations in the southern kind of hemisphere, which once again is in line with what Warner got in 2021 in its published paper in 2021. From there, kind of the more interesting part of it is the spin axis and the shape model of it. This is once again still going through the actual light curve inversion. The spin axis that we obtained was 221 degrees and negative 81 degrees for ecliptic longitude and latitude, a period that I already mentioned before. And while you might see some of this, some of this geometry right here, that isn't necessarily relevant, but what it is the actual shape of it being elongated, which is once again what we should expect for UQ, and its negative ecliptic latitude indicates a retrograde motion for it. And we're within a 2-degree agreement with Warner's result of negative 79 degrees. So why do we know that our shape model that I kind of just displayed is accurate? Over here is just once again taking those light curves that we got from before and running a fit on it based on what the shape model would produce and seeing how it aligns with observations. And most of them align pretty well, like here and here. Some of them are a little more sporadic. That's more due to the actual noise of the observation, but it kind of aligns in the same way, still giving us confidence in what we have is pretty accurate. And once again, it may not be unique, but it's still kind of giving us confidence what we're doing is right. Okay. So from there, we get an albedo termination for 1990 UQ, and using these two formulas, even though I mentioned earlier that it has an elongated shape for just a quick albedo determination, we're using the CW bandwidth and the spin axis, and assuming that it's a perfect sphere. Obviously, it's not a perfect sphere, but it's just to get an idea of what we're looking at. So using some known values and using from a published paper for absolute magnitude with it being corrected to V-band. I do also want to mention the MPC does have a value right here. It only gives an albedo difference about 0.007, so it's not super significant. But we obtain a diameter of about 0.58 and albedo 0.486 and 0.389, which is once again kind of what we expect for UQ. And some things that we plan on adding, as this is still kind of ongoing, so we want to add, somebody had mentioned it before, but we want to add sparse data from the MPC to kind of continue to add in more. We don't believe that it's going to significantly change what I kind of presented here, but it should add something to what we have, and then furthermore, the radar modeling. And that's it for my talk. I want to thank my co-advisors for their work. I wouldn't have been able to do it without them, for the conference, for accepting me, and for you all listening. So thank you.
Questions?
Andy Rifkin, Applied Physics Lab. Interesting stuff. Great talk.
Thank you.
Good job. My limited understanding of the dynamics of these things is that things with very Earth-like orbits like mini-moons could, some people think that they are ejecta from lunar impacts. Have you thought about whether the properties you're finding for this object are consistent with being lunar rocks? Have you tried comparing?
No, in the short answer. But I do think it's really interesting. I think, from my understanding of mini-moons, is that there's no direct, like, I guess, pipeline that's feeding in these objects, just kind of whatever gets captured. So it could be, it could not be, it could come from who knows where, but just from my understanding, it's more or less objects that end up getting captured and temporarily there and they get shot out. That was the point of that slide, showing that the orbits kind of get crazy when you're looking at it.
You showed that you have a lot of light curves from TRAPPIST and from other observatories and to characterize this object. So did you try to look at the shapes?
Sorry, say that again?
Did you try to look at the shape, the structure of the moons?
So the light curves that you saw, they were all of UQ. So when I was showing the polarimetry analysis, we're using the relationship of albedo and polarization. So it's not necessarily that we're getting a shape for the Earth mini-moon, but by using UQ and doing a full comprehensive shape model and getting a reliable albedo for that, because they're linked through their polarization at the same phase angle, we can kind of conclude that the albedo should be about the same. So the shape probably won't be the same, but the albedo is kind of more what we're interested in.
Hi, can you just clarify the shape model that you were showing, is that derived solely from the optical observations, or did the radar data contribute as well?
Solely from optical. So we do plan on later on, I wish that we had enough time, but that will be added later on to do the full comprehensive model with the Goldstone data that we obtained.
Thank you.
Thank you.
Okay, the final talk for our session is by Marco Micheli, and he'll be talking about ESA's Planetary Defense Office.
Keep it close. Laser? Can you hear me? Oh, yeah, now you can.
So thank you very much for having me here. This will be a short presentation of the observational activities that we do at the NEO Coordination Center and Planetary Defense Office of ESA's. It's a program dedicated to studying and presenting data to the public and protecting our planet from the threat of asteroids. So we focused on asteroids specifically as a threat, as a collision threat, not as a scientific object. Well, of course, we do science too, but it's mostly for impact. So we focus on the ones that have a non-zero impact probability. The program is characterized by three components. I'm an observer, I'm an astronomer, so I'm just going to focus on this first part, which is what we call detect, of course, observing with telescopes and detecting these things in the sky. Some of you may know that ESA will soon have its own survey telescope. This is just a slide to remind you that it actually does exist, and it will be installed in the next few months in southern Italy. But since this is a meeting on follow-up, I'm just going to leave it there and move to follow-up and how we do it. Many people here at this conference have set up networks of telescopes specifically to do timely follow-up of targets. We've kind of done the same. We have a network of a variety of small to medium-sized telescopes all over the world, designed, as it's often the case, to cover both a range in latitude and in longitude in order to be able to react to observational alerts that have a cadence of less than a day, typically hours or minutes. And of course, they do quick reaction to observational needs, but most of them actually do routine follow-up, and some of the names you may actually know. They are pretty well known now in the astrometric follow-up community, and they are responsible for a significant fraction of the worldwide follow-up. I don't want to go too much into the details of the specific telescopes. I just wanted to present some cases of observations that we or our collaborators in the network have done, just to show some challenges that are sometimes occurring when specific objects appear and need a quick reaction observation. The most common quick reaction observation that we are called to do is what we call imminent impactors, meaning we realize that some major survey has discovered an object that is on a collision course, and it's an immediate collision course, which typically means within a few hours of the time of discovery, the object will gonna hit. It's going to hit our planet. And of course, if it's less than 24 hours, we can't wait for the Earth to rotate and come around. So we have to get observations straight away. And that's the advantage of having a network. In particular, this is a case, so the second to last imminent impactor. I just wanted to present it because it has some interesting characteristics. The one I want to highlight is, if you want to determine a trajectory of an asteroid, you don't just need many observations, you need strategically placed observations. And if you have a network and not just one or two telescopes, you can observe from different continents the same asteroid, and that gives you a much better determination of the incoming trajectory. Of course, these are more objects, it's not super important, but if something bigger comes, it's actually really important to have this nearly instantaneous parallax and get it from different point of views. This is another story. Again, we care about impactors, especially we care about high priority and high probability impactors. This was an object found last year that was announced 12 hours before going into solar conjunction and being gone forever. Well, forever, being gone until the time of impact. So it was a situation where within 12 hours, we had to get as much data as we could to know if this thing was going to come back 12 years later and actually impact us. And so we did that, and we actually were able to almost exclude, most of the impact solutions. But again, if you want to do that, even for something a decade in the future, you have sometimes to react with hours of advance warning. And that's something people may not think. Is, 10 years from now to the impact, take your time, do it later. No, sometimes you can't do it later. It's gone until the time of impact. Okay, this was done, of course, with smaller telescopes, but just I want to now focus a little bit more on the faint end of follow-up. We have an agreement between ESA and ESO to use VLT to follow up faint targets, faint possible future impactors. This slide is just to give you an idea of how faint follow-up can go. Most people don't actually realize what's the faintest we can do from the ground without space assets. And 27 is a good number. We can routinely observe basically almost every month object down to 26, 27th magnitude for astrometric follow-up. Of course, they are tiny. You see a little dot there. But an 8-10 meter class telescope on the ground can do that. Of course, as we've seen, I mean, these are very competitive resources. It's not easy to get time. With LSST, this will become a problem because we can't do follow-up of everything at 27th magnitude with the telescopes we have. Can't probably do follow-up of anything at 24th magnitude even, because, I mean, not a lot of telescopes can go there. And that's the reason why I have the second slide here on follow-up, on faint follow-up. This is an experiment that I actually really appreciated the result when we tried. And it's again in the theme of what will happen when we will be flooded by 24th magnitude objects by LSST, and we can't follow them up because we need a larger aperture. Well, you really don't need a larger aperture. This is an experiment. We tried to follow up a fainter than 24th magnitude asteroid with an 80-centimeter telescope in continental Europe, in Spain. Pretty good site, but not fantastic, not world-leading site. And if you have patience, you can actually do it. 5 hours of observing time give you that. It's a signal to noise of something like 7 detection of a 24.2 V magnitude object with an 80-centimeter telescope. So this is something that I think I dare to suggest as a use case for small-sized telescopes in the future, because there's so many of them out there, most of them, some of them not even routinely used. So if you want to go faint for astrometric follow-up, of course, this is low signal to noise stuff, so it has to be mostly astrometry. But you can do it with a sub-meter class telescope, and it's actually a pretty unusual and pretty interesting case study to explore. This is just, sometimes we like to explore techniques, and this is just an example of a technique we explored. If you have an impactor that has gone lost, and you don't know what it is in the sky, people may think, okay, well, can't do anything, it's lost, we will never know if it impacts us or not unless we discover it. And unfortunately, there's a way out. The way out is what we call the negative recovery. So what I'm explaining here is another experiment we've done with VLT. And it's possible thanks to the fact that impactors actually are objects that can impact only on one of the, on a very small subfraction of the orbit where they can be in. So even if we don't know where the asteroid is, we know where it would be if it is in a collision course. So we can take a big telescope again, this is VLT, and point it at the part of the sky where the asteroid would be if it were in a collision course. If it's not there, we are excluding it as an impactor. We still don't know where it is, but this is an alternative way to do follow-up without seeing anything. It's kind of interesting and different again. I just want to conclude with a slide here. This is just a bit of an advertisement for our program. Every images we get with any of the telescopes in our network, we make them public within a few weeks, so pretty quickly. There's now, I think, about 1 million images in our archive. And they are indexed by the Canadian SSOIS system. So if you need to search any of the images of any of the telescopes that collaborate with us, you can actually find the actual original raw data there for your own science. Especially if it's not astrometry, they've probably not been exploited that much. And data is there for you to use freely and quickly, within weeks. So that's all, just a little summary. And of course, as you've seen in the map, we have a network of telescopes. There's not that many telescopes in Africa. If there's anybody who wants to collaborate with us, feel free to send us an email. We are happy to have telescopes all over the world and have access to different resources. Thank you very much.
Lots of questions. I think I'll start with
Hello. About the recovery or observation of the faint object, you mentioned you used the several rate. You had no idea on the velocity at all, or you included some knowledge of the velocity?
On which one? On this one?
Yeah, this one.
Yeah, no, this was a reasonably well-known object, so we have the velocity, actually the variable velocity during the night, because if you want to do this over 5 hours, you actually have to stack the images following a little bit of curvature. So this was a follow-up of an object that had already been known, so we could find it, we knew the motion pretty well. Of course, with an instantaneous follow-up a few hours after discovery, you may need to explore more motion vectors.
Okay, thank you.
Hey, Marco, thank you very much for your presentation. I would just like to comment on your last slide. So,
sure.
Yeah,
go ahead.
Yeah, it's
this one or
it's the last one. The
last
have the conclusion.
summary.
So yeah, so about expanding our network. So maybe this is a general question. Maybe it's also interest for our colleagues from NASA who are working on planetary defense. So we see that there is a big let's say, hall of interest in Africa. So you guys, you're doing that at ESA, and it's good. Our colleagues at NASA, they are doing that too. But this is a global challenge, but there is no plan I can see for inclusivity to get Africa involved in. So my question is, what is the best approach to do that? So do we need to I'm from Morocco, so we have observatory, we have other small observatories, and the last 2 days we have a symposium, a focus meeting about how we can use the small ground-based telescope to improve or to get Africa involved in this topic. And they see this as the planetary science, the planetary defense is one of the best science cases that we can work in to get Africa involved in this global challenge. So what do you think? So do we need to making some collaboration with Europeans and with NASA, with the Americans, to get some small telescopes and to do some kind of occultation? So because Africa is very wide and we can do these things, and also how we can, for example, providing some trainings to the younger here and providing some summer schools, whatever, to get some support from you guys, from Europeans and from Americans, to get Africa involved in this big challenge.
That's a very good question indeed, and I was at the workshop yesterday, the other one about getting telescopes in Africa and inclusivity of Africa into the world of astronomy. I remember hearing that idea that they did during DART of actually doing a campaign and then leaving the telescope there as a facility for the country where it was installed. I think this is something that should be done, maybe even more. It was really nice to see that telescope now is not being brought back by the people who brought it there. It remained as an asset, as a facility. And I think things like that should be done more. Maybe, occultations are good because they have a very localized the ground path. So you have to go there. And if you have to go there and that is in Africa, of course, there's a motivation to invest on putting a telescope there. I really hope that things like this will happen more and they will become a more traditional way of getting an instrument, getting it to Africa, introducing people to how to use it and leaving it there as a resource for the communities. And that's just an idea, of course, also in general, having ways to fund observatories that already exist through projects like this that actually do need the specific location. I think it's a very interesting opportunity if telescopes want to do it, and they can get maybe some money through Europe, through the US, thanks to their location.
Great. I just wanted to add also another entry point is IWAN, the International Asteroid Warning Network.
Yeah.
And there are periodic exercises, and if you just look at iwan.net, International Asteroid Warning Network, you can register as a member. Anyway, you can register individual telescopes too as members too. So anyway.
And it's very interesting because IWAN does campaigns that also serve as a training for observatories on how the community does observations in planetary science and asteroids. So it's actually a very good entry point for observatories.
Thank you.
Thank you very much.
And let's thank all the speakers of this session, and I think we can go to a well-deserved lunch now.
Just a quick announcement. I guess we'll reconvene in about an hour and a half. There are still a few slides missing from the next session, 2 or 3. So if you are in the next session, please just come check at the desks here. Specifically, Joe and Shinji, your slides are here, but there's some issues with access. So please just come to the desk. I have that. Yes.
I've had no luck getting my talk uploaded.
Sorry.
Am I supposed to put it on the Google form?
So I'm gonna like go get something or
Yeah, I'm gonna put it on a stick.
do you have to?
It just sits there. It doesn't go anywhere.
Oh, I'm not. I mean, because you just got in yesterday, right? Last night.
Taking in the next session.
No, the one before. But like
okay.
last night, I would really like to check before
Sort of
It's like whatever, and you are ready. But they were like that. And when you said that, you know, I was thinking we had a great New Year's of Silver today. They had one of these and then they let them hang. 2-3-year-olds.
So this was before they went to something.
Yeah. And then they all went together in bathtubs. So I think it was a really memorable party.
He's not an astronomer at all.
No, it is as well. I mean, I used to be in basic astronomy, and I my husband and I were colleagues. We were living about, I don't know, in Jena. We happened to be both in Jena from the years.
Realize I have something else to do.
No, I'm in Munich, which is close to Cologne.
Okay.
Other side.
Yeah, halfway.
Yeah, yesterday.
I was thinking, because your student is machine learning kind of stuff. We always have these summer programs for students.
Very keen.
So she could apply for something like that, which is, I don't know, I'm not quite sure. I haven't been involved in one recently. I think it's 8 or 10 weeks over the summer, and then they have week's lectures as well. You know,
Yeah, well, the weekend, there's a few people
that
pay
will
for
be really important. So she could
She's just finishing her master's writing up. December, and then she'll graduate.
Yeah, Cyril and I were talking about maybe to model up.
And then
so she could perhaps think of it next year. Because I mean, we'll get the first European exoskeleton, so we'll be the number one in Europe next year. Hopefully, at the moment it's just concrete.
Yeah, I don't know how much division meeting there is. Hi, how are you doing?
The last moment, the flight was cancelled, and there was no place in the It was a disaster.
I didn't know
Many
that.
flights were cancelled.
Okay.
Everybody have problems with the flight.
I arrived here one day like this.
No, you should speak to the speaker that was before. So I don't actually do ERI platform, it's now ERI.
You're making the one that was presented by your student.
So the data you use, right, using their telescope, and he's done like thousands of like curves. Whether he did it in
different colors.
yeah, whether they did it in multiple forms, I'm not sure.
In any case, my idea is also if you have plenty of data in your colors, in your band, I can try to do the same.
Yeah. So you need at least two colors, right?
You need the two colors in the three bands.
Yeah.
Okay.
All right.
We will be in touch.
Okay. Thank you.
Thank you. Yeah.
Yeah, I think the FAA will get some of the sessions that's going to take some, but they get there. Sorry.
finger.
But at worst, I will also announce it at the end of that session.
1, 2. Hello, can you hear me?
to join the Zoom?
Hello? Hello, can you hear me?
Yes, we can hear you.
Hi, Nick. How are you?
Could you share your screen, Salon?
Yes, let's go. Is it okay?
Oh, hang on just a second. Welcome, everyone, to the afternoon session, Observations of Faint Distant Targets Beyond Visible Wavelengths. Our first presentation is virtual by Javier Locandro, Enhancing LSST Solar System Discoveries, the Critical Role of 10-Meter Class Telescope Follow-Ups. And this is an invited presentation. You have 20 minutes.
Okay, thanks a lot for your invitation. Can you see my arrow moving or just to know?
Yes.
Okay, perfect. So the idea is to talk about the role of the largest, largest telescopes in the world to follow up the most interesting target of that the Vera Rubin is gonna discover. So let's start. I think that everybody already seen this table. LSST will increase the number of known objects by an order or more than an order of magnitude, which is a huge increase, a big step. That it is probably the largest step since other surveys started to operate in the past. But always the same is we have the same thing. We increase a lot the number of objects we know in our solar system, and when they happen, we much better know the structure of the solar system. We discover new, very interesting and faint objects. We discover new kind of objects and new populations. So we had to be very much prepared, not only for the populations we know, that means the NEOs, the main belt asteroid, the Jupiter Trojan, the Trans-Neptunian, interstellar objects, the comets, and the active objects. We will also have to be prepared to study a lot of a very huge number of them in the future, because the expectation is that we will have the coverage of more than 1,000 objects solar system objects per night. That will be also competing with 10⁷ transient alert per night. It's also interesting to plan the activity of this follow-up, to know that the LSST will provide very accurate colors in the visible from U to the Y band. So we have to see what else can be done. There's no way to compete with the LSST for the 10-meter telescope in mapping populations. This is gonna be done in colors by the LSST. But what make they need is a rather obvious answer. We need to follow up and physical characterize the most peculiar or the most important object that LSST will discover. And we need 10-meter class telescope. We need similar class of telescope because we will be observing likely very faint objects. So we need to increase the sensitivity and resolution, increasing exposure time, for example, and doing spectroscopy. So the spectroscopic capabilities are going to be very, very important. Also, we can go to the near infrared and obtain some information in the near infrared, extend the temporal coverage, and what is, I think, even more interesting, we will use different observational strategies. We can produce dense light curves. We can go much deeper, increasing the exposure times, and etc. Actually, there are 13 of such telescopes operational in the world. Fortunately, we have telescopes in both hemispheres, and they cover a rather wide range of longitudes, from the telescopes in the Canary Islands to telescopes in the longitude of Hawaii. We have a rather good wavelength coverage, but be prepared. With a 10 to the 7 transient alert per night, the competition is gonna be very hard, right? So prepare ourselves with good proposals and prepare to take advantage of every minute you can get in these fantastic machines. What is the kind of science we should be prepared to do with the LSST discoveries? In the case of near asteroids, for some of them, in particular for those that could be in impact trajectories, the small impactors, we should be prepared to do follow-up astrometry and any kind the properties we can also retrieve from the 10-meter telescope observations. Also, it's likely that the population of very peculiar NEAs is going to be increased. ATIRAX, for example, the discovery of Earth Moon Trojans, for example, mission targets, etc. We will also be able to follow the activity of active asteroid at active centers, and maybe activity even at further heliocentric distance. And for it, we need to attain very high signal-to-noise ratio images I will see later. The study of extreme TNO population that used to be very faint, we can also be able to detect inner or cloud objects, and why not Planet 9? Also, the detection of objects in impact trajectory with giant planets. Why not expect to have a Shoemaker-Levy 9 event again, or not that spectacular, but something that we can study now with much bigger telescopes. Or cloud comets that came with a large perihelion distance to allow us to study objects not very much affected, comets not very much affected because they didn't ever enter the inner solar system. The increase in possibilities of detecting interstellar objects also is crucial. And as I said before, we should expect to find new population of objects that need to be studied in the next years. Well, Marco Micheli talked about this earlier. In fact, he has much updated information than me on the VLT program, but 10-meter telescopes are absolutely needed to detect very faint small near asteroids in impact trajectories. And I should say also that to study the very ultra-fast rotators, something that I asked in a previous talk, is very big telescopes are going to be needed in the case of these very small, very interesting near asteroids. So there are a lot of examples of the science we can do. One of these is the detection of potential impactor and its characterizations. In terms of activity, and I'm sorry for using biased example, kind of example using the science most of the science we already did, but it's an opportunity to show our work. We run a very productive characterization program to observe active asteroids as soon as they were discovered. We used a TO solve mode with the 10-meter GTC that was very successful. We were able to observe 18 of these objects and publish 13 papers where we characterized activity, measured the dust coma properties thanks to the combination of high signal-to-noise images and dust Monte Carlo dust models, and determining this way the activation mechanisms. We were able to determine which collisional activation, splitting or rotational disruption, or sublimation, like what we actually call May-Med comets. Also to study the nuclear size, and using the spectrum, we can also try to detect gas species. So we need to have rather high signal-to-noise, low-resolution spectroscopy, only feasible with very large telescope. Imagine that we will determine activity at even lower level with we'll discover objects in much lower level activity with LSST than the actual ones. Also, the spectroscopy of extreme TNOs is almost impossible with a small telescope. We need to use 10-meter telescope to have the visible spectroscopy of these targets that are extremely interesting to study this population. Some examples of objects observed in 23 or 24 in low-resolution spectroscopy, also with the GTC are shown in this picture. Another example of the science we have to do with these objects are the physical characterization of interstellar objects. In the case of 1Y Oumuamua, 10-meter telescope like VLT, Keck, and Gemini were very important to determine properties like color, rotation of the targets, and so on. Even they were able to observe during a very short time span. So we need to have a rather fast response with our telescope. This is a crucial thing. It's not in most cases it's not necessary to have minutes or a few hours. Sometimes for most of the program, few days are enough, but not for all, of course. But we need to put programs in our telescopes to do this kind of observations for this kind of objects. Another example is the 2Y Borisov, with the spectroscopy obtained with the GTC and imaging that allow it to determine the spectral properties, the detection of gas species, showing that the comet is this interstellar comet is very similar to our comet, so likely similar composition and behavior. Then we can go to the near infrared, and some examples of Borisov in the near infrared are shown in these papers by Yang et al., Fitzsimon et al., and Hugh et al., using Gemini and VLT in two different resolutions, low resolution and rather high for us. Solar system astronomer, this is a very high spectral resolution. But in the case of the near infrared, we need to start to discuss about the kind of spectrograph we have. Actually, the largest telescope all have some kind of low resolution near infrared and visible spectrograph, but not as low resolution in the case of the near infrared spectrograph as the one we need to have a resolution of about 100 is not usual now. That's not the case, for example, of the GTC. And that is why some people, for example, suggest to have X-shooter-like instruments that also can do visible, but you can go from visible to the near infrared with very nice or rather nice resolution and signal to noise. I would like to have something like the NIX instrument, the one I had when I started to observe TNOs in the 3.5 meter Italian TNG telescope in La Palma. Such kind of a spectrograph in a 10-meter telescope can be a very nice machines, but unfortunately, I don't think there is any plan to do that. But as probably Noemi will explain in her talk, actually, it is impossible to compete with the James Webb. So for the most interesting cases, James Webb is gonna be the telescope that is gonna be used to study in the near infrared, and the priority in particular in spectroscopy is not gonna be easy to get useful or very good quality data of objects in magnitude 22 or even fainter. So we can do that with the present instruments up to 21 or so. Going fainter is going to be very hard, and the quality we already know from the TNOs that it is not that good, but only for the very bright ones. But if we have to prepare our knives for a 10-meter telescope or James WST, we need an order of magnitude more knives because of the difficulties to get time in this telescope. But I'm pretty sure that for very interesting targets, it will not be possible. I would like to finish the presentation talking about some very instrument kind of instrument I think that are very well suited for follow-up in 10-meter telescope, in particular of the very faint objects. The instrument that can do simultaneous imaging and different filters are very nice for this kind of science. That is the case of the Hypercam camera that is installed at GTC and soon is going to be a common use instrument. This is a very sensitive instrument that allow you to take images simultaneously in UGRY and SERA filter, but that goes very faint, in particular in the UNG, that it is very interesting for studying, for example, hydration. And I think that this is the kind of instrument that will be very useful for follow-up this kind of targets. And I saw that at least in Gemini, I don't know if there is another prepared instrument or planned instrument for other telescope. In the Gemini, a similar instrument that will observe in 7 different bands from visible to near infrared is going to be installed hopefully soon. So to conclude, 10-meter class telescopes are absolutely needed to follow up on physical characterize most of the peculiar and interesting LSST discoveries. Rapid response mode, such as TAO, very fast or not that fast, DDT times are needed, and that should include different kind of objects. We should ask for programs that include all these kind of instrument objects, and in particular to leave them open to new kind of objects are needed, and also long-term monitoring program for these new targets. That probably these objects are unknown when the proposal is written. And finally, imaging and low spectroscopic instruments are necessary. I will finish here, but to end, I would like to thank Elena Mazzotta Spifani and Olivier Naud for their help in preparing and comments in this presentation and their comments. Thank you very much.
Thank you, Javier. Do we have any questions? Okay.
Andy Rifkin, Applied Physics Laboratory. Great talk as always, Javier. I guess my question is, you mentioned the near infrared. Do you have any thoughts about longer wavelengths? Like you said, JWST is hard to compete with, but on the other hand, there is only one JWST. It can't look everywhere in the sky, and if you've got 10 or 13 10-meter telescopes, do you think it's worth? I guess that's two questions. What do you think about longer wavelengths given that about the JWST?
Oh, to be honest, I'm not very update on the longer wavelengths in 10-meter telescopes. Maybe you probably know much better than me about that. I'm not user of most of this telescope and not updated. Would be very nice to have some specs like instrument in one of these telescopes. But I really don't know if there exists one of them. For sure, if we were able to go up to 5 microns, it is very nice. The problem we both know very well. It is very hard, very difficult, and in any case, it will be limited to, let's say, be equal to 2021. I don't think that even 22 we will be able to do good science with. But to be honest, Andy, maybe you probably know much better than me these instruments in this telescope.
Okay, anyone else? Online? No? Okay, we thank the speaker again.
Thank you very much.
So as far as we know, our second speaker is not here, but to stay on schedule, we could have questions from previous talks, if anyone has an additional one from this morning. I could start earlier. There we go.
This is a question actually I had a chance to chat with Jean-Baptiste about, but I'm curious for the observers here, if you see any conflicts or potential confusion for people who are using the older VBRI system versus the more modern narrow fan with the G filters, and you're trying to do color differences. Are those directly comparable, or is there a chance that things classified in one pair of colors might be slightly different from classified in a different set of colors? I'm just not familiar enough with the differences to know if this is an interesting or an important thing to keep track of.
May I answer?
Yeah, I'll take a swing at it, but there's probably other folks that, there are, the filter transformations are pretty well known. Yeah. I think a lot of the work that's been done that I've seen since the Sloan survey, whenever that was, probably 20 years ago, have been in those colors. My sense is that the observational uncertainties are going to be large enough that they're going to swamp the uncertainties due to switching from one filter set to the other. But and of course that's going to depend on the brightness of the object. So with the fainter objects, that'll certainly be true.
Yeah, fully agree.
Anything else? Or online? I can start on my presentation.
Okay, due to a slight oversight, I assigned Anne as chair, and she's actually presenting in the session. So she's going to start her presentation, and I'm just going to take over for one talk. She'll start slightly early and then overrun slightly because she has some interesting slides to show us to the end. So she will use some of this slot's time in her presentation.
Okay. So good afternoon, everyone. I'm happy to be here to talk to you this afternoon about the New Horizons search for targets in the outer solar system and the follow-up observations results that we have so far and future plans for continuing with this search. So New Horizons has enjoyed a unique perspective going through the solar system since launch in January 2006 and a Jupiter flyby in February 2007, the Pluto flyby, of course, in July 2015, and we had Arakoth in 2019. What is primarily unique from this perspective is the large phase angles you have access to from the outer solar system. So this is the only NASA's observatory in the solar system, in the outer solar system that can observe these objects at these large phase angles, and also the close proximity helps you as well with close flybys, and we observe objects as unresolved point sources, but that also allows you to take advantage of those large phase angles. So the team began searching for an extended mission target even before launch in 2004 and 2005 using large ground-based telescopes, primarily the Subaru telescope, but have used others, Magellan as well, and searching from 2004 through 2013 found nothing that New Horizons could have a close flyby of. It took using the Hubble Space Telescope in 2014 to conduct a dedicated search for a Kuiper Belt flyby target that New Horizons could reach. And in the red square there on the upper right are the first 5 images ever taken of Arakoth, the flyby target. So that resulted in, of course, the close flyby and all that affords with the instrumentation that New Horizons has on board. So we would love to have a second flyby target, so we are continuing this search. In addition to the close flyby, of course, we can do the unresolved point source observations. So now we are primarily using Subaru with its hypersuprime cam to conduct the search for a flyby target if we could find one, but other objects that New Horizons can look at. So here is hypersuprime cam at the prime focus of the 8.2 meter Subaru telescope. It's a massive object, or a massive camera, taller than a person and has an enormous field of view on the sky. So this gives us much more capability searching than, say, Hubble would. We can't redo the Hubble survey because really the WIF3 camera, it just has too small of a field of view to be practical at this point to search for a flyby target. We purchased a new filter for hypersuprime cam, HSC, that encompasses all of G, R, and I, where previously we'd just been using the R band. So this new filter has been in use since October of 2022. However, that really wasn't a great time to be looking because the search field was low in the western sky. We only got quarter nights at that point. We used it again in 2023, and we just finished up a run earlier this month, last week, in 2024, so the data analysis of all of that is ongoing to try and find targets. This is what a single 90-second star-subtracted image looks like from HSC, and some of the pointings we use in previous years are up in the upper right. Stacking all of the 90-second images in a single night of observation, generally these are half nights of observation, results in images like this. So this is a lot to sort through to try and find new KBOs. So we've originally we used human searches, and from just one run had more than 44,000 images to sort through using the images or examples of those searches. Are shown at the bottom there. So the left two most are actual targets. and actual KBOs, and one that would be rejected is over there under the red X. But really, machine learning is more appropriate to apply to this effort. So we are using a machine learning pipeline, which actually is the LSST solar system pipeline. So it's being put to use already, using shift and stack techniques to find KBOs shifted at the appropriate rates for objects, beyond 30 AU, to try and find real sources. So this is done. From 2021 and 2022 efforts of searching with Subaru, this is a summary chart of all the objects detected. Their color coding is by year. So most of those are in the classical main belt of Kuiper belt objects between 30 and 50 AU. Those are all currently in New Horizons' rearview mirror. The spacecraft cannot look at those. The spacecraft position is shown here at 50 AU, the black dot. So there are some in the ahead of us that it could look at if they were close to the spacecraft when it approached them. We're going to be at 60 AU in October of this year. So there is a brand new paper just out by Wes Fraser in the Planetary Science Journal. This is one of the figures in that paper summarizing the more than 240 KBOs that have been discovered by this search effort with hypersuprime CAM. This is an excess of objects beyond 70 AU. The OSIS++ model predicts that there would not be this many. So is this a new population of KBOs beyond the already known Kuiper belt? Hard to say. We're sorting that out. That's one of the conclusions of the paper, that this is certainly a possibility. An independent analysis was done by Fumi Yoshida in her paper, also published earlier this year. And her discoveries are included in that total. Another piece of the puzzle comes from New Horizons' own instrument, the Student Dust Counter, SDC, which has found increases in the dust flux measured beyond 40 AU than models would predict. Those points over here that are above these model prediction lines. So what the source is of this dust beyond 50 AU is very much in question now. It could be an indicator of this additional population, but that's some of the things we're working on solving right now. So New Horizons has already looked at some of these Subaru discoveries at high phase angles. There have been more than 30 KBOs looked at by New Horizons from all different dynamical classes. I don't have time, well, in 10 minutes, I thought I had 10 minutes, not time to go into a lot of the science from those analyses. But going further out into the solar system, really New Horizons is going to be sampling the scattered disk objects. It's really pretty much done with the classicals. But some of these have very interesting locations. Here's perihelion distance versus aphelion for most of the objects already observed, but there are a handful that are still yet to be observed that extend beyond the termination shock and beyond even the heliopause. So it's an opportunity to study space weathering on surfaces that are exposed to different environments than those closer into the sun. This is a summary of some of the work that's been done. On these KBOs, we can determine shapes and surface photometric properties from being able to observe them at these different phase angles. So here are examples of classical KBO light curves at different phase angles because their irregular shapes have different amplitudes at high phase angles. Some do, some don't. And then their phase curve shapes are quite different as well. And what New Horizons has found is those differences in shapes correlate with, so far, surface composition among the different objects. This effort, finding all these KBOs and studying them with New Horizons, also enables the opportunity to observe them from Earth during stellar occultations. And Simon Porter in 2022 published a paper with 66 different events possible to observe of objects that New Horizons has looked at, upcoming or some of them already passed in 2021, but all the way up till 2029, using the new astrometry provided by New Horizons, because that gives you another astrometric data point on their orbits. So a single positive chord from some of these occultations can constrain their size and albedo, which is very helpful for the photometric modeling. Multiple chords can reveal the shape, as we did for Arakoth, finding out that it was a contact binary before the flyby. Just an example of one of those occultations went across the southern portion of the African continent earlier last month. That was from the Porter et al. Paper. But an example here is a remote telescope observing multiple occultations just automatically during a night. And we did just bring one of those to the University of the Western Cape to do these types of observations. So hopefully this could be set up by students and run soon to learn more about these distant objects that New Horizons has looked at. But should we get really fortunate and find a flyby target, I can guarantee there will be an all-out effort to do stellar occultation campaigns. And we have literally an army. This is 100 telescopes set up. Each one of those dark boxes you see there is equipment for a single telescope, 100 of them in a warehouse ready to be deployed for a flyby target should one be found. And I'll just conclude saying NASA has extended the New Horizons mission through fiscal year 2029, and at that point New Horizons it will be about 75 AU from the sun, but nothing's stopping it. It's going to continue on to the termination shock and then on to the heliopause, just like the Voyagers did. But New Horizons does have more capable instrumentation than the Voyagers were equipped with. So the heliosphere folks on the mission are very much looking forward to those events happening upcoming. And we're also looking forward to the discovery of more KBOs that New Horizons could look at. And I will finish up there and take questions. Thanks.
Thank you, Anne. Questions?
If LSST finds something in the right direction, is that in time for you potentially to reach that as a target?
It could be. I mean, what we're planning to do is conserve all the resources on the spacecraft as much as possible going forward. So as many hibernation periods as we possibly can, because a flyby could happen in the 2030s. The spacecraft has enough power to go till 2050. As far as fuel on board, it probably only has enough left for one more close flyby, if an object could be found. So we are planning to use LSST, if at all possible, to continue doing this search. And beyond that, looking at Roman as well to do searches, because Roman will have a good wide field of view. So Subaru is kind of ending as far as a search tool, and new things coming online will be used to keep searching.
One more.
What about ESA Euclid?
We did look into Euclid. That has kind of been left by the wayside. I don't really remember the details on why we really haven't pursued Euclid as aggressively. I think we were hoping to get in on some of the commissioning observations and hoping that those pointings could help us. But I think most of the pointing with Euclid is being done polar observations. So looking in the ecliptic wasn't really part of the plan. So I think our use of Euclid would have been too much of a disruption for at least its main observation plan. There was an opportunity with commissioning, but there were issues with getting Euclid up and running, so that kind of passed us by. But we did consider it, certainly.
Hi, Amanda Sikafus, Planetary Science Institute. You, I think, have been involved with quite a few occultations in support of the Lucy mission. Those would be Trojans. I was just wondering if you could say anything about those efforts.
Yes, in fact, one is going on right now as we speak. I have been participating in most, if not all, except for this one, occultation efforts to observe the Lucy targets. Those are ongoing, but this, I believe, is the current campaign, which is for Patroclus and Menoetius, the binary that Lucy will visit in 2033. This is one final campaign for that target, that system, and as far as these mega campaigns to get Lucy occultations, this is kind of the last hurrah. But there have been many, several of them in Africa. We had several events in Senegal. I had a poster on Wednesday about those events. We had one in Senegal for Arakoth and two in Senegal for Lucy. One of those happened during COVID, so actually no one could travel, and the Senegalese, local Senegalese had to step up and do that occultation all by themselves, and they got a result. That was Polimile, one of the small Lucy targets, and later we did an Orus event, and that one coincided with the Lucy launch. So I ended up going to Senegal because the Lucy team members wanted to be at the Lucy launch instead. But yes, there have been many, many opportunities for African participation in these occultation events, and I hope that there are many more.
We thank the speaker again.
Thank you.
Okay, the next presenter is Susanne Falsner, and the talk is titled "A Stellar Flyby Explains Multiple Small Body Properties in the Solar System."
Okay. Whoops. So this session is called Observations, but let me take you in this talk to theory. And what I want to present you is a new hypothesis for the origin of the TNOs and the irregular moons. And Anne's talk made me really happy, and in a few minutes you will know why. Okay, beginning from the start, the solar system formed from a flat disk of gas and dust, and the TNOs are the remnants of this process, and they're basically the witness of this past. And as most of you know, most of these TNOs move on eccentric inclined orbits, and the standard explanation for that is that the TNOs are planetesimals that were located between the planets. When the planets moved, they were scattered outwards, and a few of them got captured in the Kuiper Belt region. This is a so-called Nice model or planet scattering model. But there's a few unexplained objects, for example, the Senna-like objects, which are at extreme distances, so that they can't have been scattered by the planets there. Another one are the retrograde TNOs moving in the opposite direction than the planets. These can't be explained within the Nice model. So there has been extensions to the Nice model, and the most popular ones for explaining the Sedna-like objects are Planet 9, which has so far not been found, and a stellar flyby. And what I want to present you is that a stellar flyby can actually get all the populations. So it's not an add-on, but it's a standalone solution. And here I show you a simulation of a stellar flyby. You see the solar system disk, which is initially much bigger. It's this one in the simulation is 150 AU. And then you have another star going by, warping basically the disk. And then you see in the fifth panel, if you start counting like that, you see the end state, and the last one is a zoom out of that. So we have not done one of these simulations, we have actually done 6,000 of these simulations, and we vary the periastron distance, the mass of the perturber star, the inclination, the angle of periastron, and looking for the perfect match to the TNO population. And we actually found a candidate. And that is a perturber with a mass slightly lower than the sun, with 0.8 solar masses, and at a perihelion distance of 110 AU. And I think I've gotten now two. Okay. So what we look with is for quantitative, not a qualitative, a quantitative match of the hot Kuiper belt population, of the cold Kuiper belt population, the Sedna-like objects, and the retrograde TNOs. We are not looking for the retrograde TNOs. We mainly do the Sedna and the cold Kuiper belt. And this is actually what we find we found them all in the right quantities at the right locations. Okay, so simulations have the tendency to just reproduce. We think this is not good enough. We make predictions. Okay, from our model, we would predict that there are more objects beyond 60 AU. This is why Anne made me really happy. Okay, that there are more high inclination objects and more retrogrades. And when I say more, I don't mean, you know, LSST will get more, but it's relative numbers to the populations we have at the moment. If you think of the retrogrades, there are 2 at the moment. If you see the Sedna-like, it's 3 at the moment. The relative numbers should go up. And LSST will provide an immediate test to our predictions. So what we can do as well with that is that we can trace back where these populations come from. And normally people think it's just a question of distance to the perturber star. But you see, it's a very, very complicated pattern because it's the sun, the particle in the disk, and the perturber star. So you get really this kind of pattern. And the region inside Neptune remains completely unperturbed, while the other one is completely mixed up. So this can eventually be used to determine the properties of the primordial solar system disk. So we will really be able to look back 4.5 billion years if this model turns out to be valid. So while this flyby is happening, we found that about 70% of the disk material gets injected into the inner disk. And it depends a bit on how big the disk was. So we have here 2 examples, 150 and 250 AU. But what you see is there gets always stuff injected right into the solar system. So the nearest object we have is at 0.07 AU. This is really far in. And then we thought, okay, in the NICE model, they say that the irregular moons got captured. We get injections as well. What would we get? And I first got a bit worried because when I looked at these objects, most of them were retrograde. So you would say, okay, this is fine, this is fantastic. I didn't know anything about irregular moons before, so I was first worried. So I was really happy to see that this is the case. So we would actually have an explanation why there are more retrograde than prograde objects. And that would only hold for Jupiter and Saturn. Further out, it changes a bit. And what we get as well, we get an explanation why there is a lack of very red irregular moons. And the reason for that is that these injected objects come all from outside 60 AU. So for us, we assume that the cold population is the inside. This is very red, and then it gets grayer if you want. So for us, that there are no, very few, very red irregular satellites would be just, you know, normal because it comes from the outside. So, in summary, a specific stellar flyby can produce the hot Kuiper belt, the cold Kuiper belt, the Sedna-like objects, the retrograde objects in the right quantities at the right places. And the TNOs injected during the flyby could explain the dominance of retrograde irregular moons and as well the lack of very red irregular moons. Thank you.
Thank you, Susan.
Thanks for an intriguing hypothesis. Does your model have a prediction of when the flyby might have occurred?
This is actually a very tricky one because, I mean, I come from a completely different field of planet formation and influence of the surroundings. And there you have in a cluster, you have most close flybys, or the frequency of flybys is highest very early on. So this is a good bet, but taken that we had 4.5 billion years, if you add that up, you come actually to more or less the same number. But there could be a way of determining that. What you should have criticized, so somebody should have said, what we haven't got in that is retrogrades. Retrogrades, not resonant ones. The resonant ones come only over time. They only develop over time. So we've modeled the first giga-year, and we see them coming up, and we haven't got enough yet within the first giga-year. So it might be actually possible to determine when it happened from when the resonant population is right. But that will be a uncertainty of 1 giga-year, so okay. It's not perfect, but it's a way to get there.
Okay, we have an online question from Ivan Lyusarev. The Jupiter Trojans capture was included in the model?
We didn't talk about the Trojans, but in principle, it's the same as the irregular moons. We just started with one population and will go now through the others. But because it works for the irregular moons, there is a high chance that it will work as well for the Trojans.
Okay, sorry, we don't have enough time, so you can ask the questions to the speaker later.
The next speaker is online. Could you share your screen, please?
Hello, I think so. And let me lower my hand. I may be the first speaker that has a question in their talk, because I found Susan's presentation very interesting, and I would like to ask her one thing. You will know why during my presentation. So let's share the screen. PowerPoint here. Can you see it?
Yes,
And you are hearing me, I
slides are up
guess?
now. Thank you.
Okay, so let me hide, okay, the panel. How do I hide this? No, everything is hidden. Okay, so this is Noemi. I'm giving my talk virtually from nowhere because I'm in the process of moving from one continent to the other. But I found this focus meeting very interesting. And also, I mean, we have so many cool results that are starting to come with GA that I think is really amazing to have it in as many conferences as possible, so that to spark conversations, because this is just beginning. This is the dawning of a new era, I think. So let me go to the next slide. The main motivation to do spectroscopy, that is what we are doing, from about a little bit below 1 micron to 5 microns of TNOs. Well, first, because it couldn't be done before, well, that's always like a motivation. It's some light that we were missing that we couldn't see, but also because, you know, there were many proofs. These are all images of TNOs, some of them captured by planets, some of them in the form of small comets. And with these images and many other observations, we're showing that the TNOs were really diverse. And I mean, we go here from Triton, Pluto, Phoebe, Arrokoth, Churyumov-Gerasimenko, but also 30 years of photometry were showing some clues, were showing differences in colors, in the visible mainly, also in the near infrared. And for 30 years, we were the specialists in photometry and in formation of the solar system and everything, were trying to trace these differences in color into compositional differences, maybe, but only maybe because photometry does not allow you to really do compositional studies. And tracing that to specific locations or some kind of history of the formation and evolution of the solar system. And all of that has been a really good ground to grow from. But what spectroscopy was telling us, I've been doing spectroscopy of TNOs for 20 years, was a little bit different, because there was a lot of diversity in what we could see with our eye and with the spacecrafts, and a lot of diversity in colors, but the spectra were just showing differences in the continuum and water ice. There were a couple of objects, really large objects, the dwarf planets, that were showing a lot of methane, 2 objects that showed methanol, 3 with arrow code, and just Charon and others that show clues and hints of having maybe nitrogen and CO. All the other that we were putting on our modeling efforts to explain the surface composition of the TNOs were silicates with no absorption line or absorption feature in the visible and near infrared, and complex organic material. Both of them, we use them as coloring agents, but there were no specific features that could really tell us that those materials were up there. So in 2017, when we prepared the GTO proposal, and in 2020, when I prepared the DISCO proposal, we were full and filled with hopes. Our expectations were high. These are plots that I included in the DISCO proposal specifically to show that we were expecting to find CO2, and that we were expecting of having a lot of differences from 3 to 5 micron, depending on which kind of complex organic matter we would have, or maybe having some HCN, or maybe some nitrogen. So we had a lot of expectations for a big feast, but it was only expectations until in 2023, we started receiving spectra from Webb. And this is just an introduction to open your appetite. DISCO observed 59 TNOs with the same kind of observation, just near spec, low resolution, 0.7 to 5.4. And the spectra started coming during 1 year, 1 here, 2 there, 3 there. So we could already see that there was differences in the spectra, there were differences, but also there were similarities. I mean, you can compare these ones here, you can see my cursor and see that they are pretty similar, and that they are different from all of these here, but all of these are also very similar, and different from this one here, but all of these in this column are very similar. So there was something happening. And with our eye, we started identifying spectral groups and interpreting them in terms of composition. Finally, thanks to Webb, we can do compositional studies of TNOs with a lot of different absorption lines that can really confirm us what is up there. So the first group that we identified, we call it bowl because of the shape of these 3 micron bands. And it's basically water ice bands at 1.5, 1.65, 2.0, 3.1, the Fresnel peak, very clearly seen here, indicative of crystalline water ice, and this broad band here that is also water ice. Okay, all of these are indications of water ice. We also have CO2, clearly seen at 4.27, but not the combination bands or the other overtones here at 2 microns. So it's a lot of water ice, but it's not only water ice, because these objects, when we check the albedo, the geometric albedo of these ones, are the lowest albedos in the trans-Neptunian population, at least in our 60 objects. What means that there is, again, something hiding here that probably does not show an absorption. Also, we think this one here is an indication, and actually, of olivine. And actually, when we try with our models, we need to put a lot of silicates from 30% to 70% to really match the albedo and the spectra of these objects. So this is the first group, but this is the second group that we identify, and this is the most abundant one. and is characterized by these absorptions here. We call it double dip because of this double dip, one dip, two dips. This is CH stretching, so aliphatic, complex organic material, and all of this here is CO2. We don't only have the fundamental band of CO2, we have weird scattering effects that produce these peaks and this absorption here, and we clearly see 13 CO2 absorption. So all of this is CO2. Here and here, you can also see the combination bands of CO2. And this is important because I will talk of this later and in many other talks. We have a 1.5 band and we have a 2.0 band, but they look really different from the bands of water ice. So these bands here on the most abundant group, we don't think is all water ice. There can be some water ice, but we think we need complex organisms to really reproduce the shape of this. So the 3 microns, it doesn't show the Fresnel peak, crystalline water ice as the one above. We think it's more OH, maybe some A8, NH, and the same for this here and here, and methanol here. I will talk on that later. Then we have a lot of carbon monoxide related to the carbon dioxide, and we have also this clear absorption here that we identify with OCS or CO3. The third group that we have is the cliff one, because the reflectance goes really down and it doesn't really come up again. Has also a double dip, but it is not dominated by CO2. The CO2 band is just Gaussian. It's very similar to the one on the bowl type. And sorry, one moment. One moment. So this other one here, the cliff, it's a way more complex spectrum and shows clearly methanol bands. It shows complex bands here, here, and also the OCS. So we have 3 groups that are compositional groups, and we can clearly trace to the materials that are making them different. But to confirm this with measurements, how do we do that? So we do it in 2 ways. One is to run 3 different clustering techniques. Here on the left, you can see the results of one of them. The 3 different clustering techniques are all compatible and they give, not compatible, consistent. They give the same results and separate the bowl, the double dip, and the cliff. But also we do another thing, and it's okay, let's measure the area of the bands of these materials that I have said that characterize the H group. The water ice for one, the CO2 for the other, and the complex organic matter and the methanol for the other. And we measure this area in each single spectrum, and we get something like this. And this is what allows us to tell what we think is the scenario and the story of why there is so much diversity in the trans-Neptunian object and how this diversity is organized in groups. And it's because the ice lines in the location where these objects were formed. So that's why I really like the talk before, because they are talking, Susan was talking about tracing the location of the TNOs where they formed in the disk. So the main ice lines that cause the differences in the 3 groups is the water ice retention line, of course, for all the bowl. Then when the CO2 heats, in comparison with the H2O, is way more reactive and produces a lot of things. So we have a lot of CO2 and we have a lot of CO also for all the double dip. And then we can cross one or many other ice lines, like for example, methanol one, hydrocarbons, CO also, or nitrogen species. And then we get the diversity that we have in the cliff group. So I think for the first time, we have really compositional evidence that explains the gradient or is related to the gradient in the primordial planetesimal disk. And I'm going to show you now a sequence of slides with different representations of new facts about the solar system that we will have to start having clear in our mind. So the widespread of water ice that we thought it was the only material showing on all these objects is not really, does not stand up really more, because the 1.5 and the 2.0 micron bands, not all of them in all the groups are caused by water ice. So we have water ice rich objects, Haumias. We have water ice surfaces on the bowl type with silicates. And then we have water ice poor that are the double dip and the cliff. They may have some water ice, but they are not dominated at all, not compositionally and not spectroscopically by water ice. But we have some material that is widespread, and is the CO2. We clearly can see it in the three groups. We can see it in every single object in our sample. And related with the CO2, it comes the CO. The objects that have more CO2, they have a lot of CO also. That is probably an irradiation product of the CO2. So as a first order, the relation between the H2O and the carbon species, and the relation between the carbon species and the CH, NH, and OH are the lines that are marking the differences in the Transneptunian population, and we clearly see methanol influencing at least one of these groups, or a subsample of one of these groups. So this is just to show you the differences between how complex organic materials, tholins, that we call, have bands at 1.5, 2.0, and have a blue continuum. That is what we see on the double dip and the cliff, and how Enceladus or circuit wave is very similar to our bowl type, but the bowl type is kind of reddish because of these silicates that are mixed with the water ice. Then here we see how the differences in the 3 micron bands, that they appear in the second dip here, caused by methanol and by complex organic matter, that are all of these black lines here that show a lot of diversity. So this band is going to be more NH or OH more than H2O for the double dip and for the cliff. Then this expresses the widespread of CO2, 98% of our sample, and 50% shows CO here, very volatile material, but present on 50% of the TNOs that we studied. And we had a good representation of the different physical parameters in our sample. Then, this is for the methanol. We compared it with a rocket from New Horizon. Remember that when methanol was observed on a rocket, before that, we were thinking that we would have methanol on objects with water and complex organics, like Pholus. That was the only object before with a clear detection of methanol. A rocket was different from Pholus because it didn't have water ice. But now that is kind of the common rule for methanol, because our objects with more methanol here at 2.27 and 2.34, these are the ones that have the 1.5 and 2.0 due to complex organics and not to water ice. So methanol is more associated with complex matter than with water ice. And then there is another band at 3.9 of methanol that we can also see it in these objects. And we will talk about this later, because there is a work in progress where we study layering on the surface and irradiation products related to the methanol. So this is the basics of our DISCO ice lines paper that will appear sometime. It's being published in Nature Astronomy, and it takes a little bit longer than others, but it's already on in the process, in the line. But we are working on many other papers for the second batch, and this is going to be important because where they formed is very important, but also we want to trace evolutionary effects. So Javier Lecandro is studying the centaurs with a GTO and DISCO sample. So in thermal processing, we are studying on the bowl effects of irradiation and the relation of CO2 with amorphous water ice. We are studying the methanol and the layering in Brunetto et al. There are some GTO works already published on the Eris and Makemake, and on Senna, Gongon, and Kwawar, the largest TNOs that show different irradiation regimes, so that impact the surface also. And then we have this amazing spectrum that is my next favorite things with Webb, that it will appear in a couple of weeks probably, and it's already in the archive. And it's GTO observations of Chiron. We knew Chiron was special. Chiron has been seen active at large heliocentric distances, as large as 18 astronomical units. And it had an outburst in 2021, I think. So when we observed it in 2023, Chiron is still active. You can see here the coma that is oriented in the direction of the sun is clearly related with activity in the subsolar point. These are some slices where we don't see the coma. Here we really can see it, even some rays in the opposite direction of the solar direction. And the spectrum is amazing. I mean, It shows things that we have seen: a blue shortest wavelength continuum, absorptions at 1.5 at 2, at 3 microns, CO2, but let me show you some differences. So we clearly see fluorescence of methane ice here in this wavelength range. All of these peaks in emission, they correspond with fluorescence of methane. So we have methane gas in the coma. And the CO2, this is a double deep spectrum, and this is the recent result from Harrington Pinto with James Webb observing CO2 emission monotherma. Our band, that is this here, it shows the characteristic absorption and peaks of a lot of CO2, and it doesn't show a deep absorption at 4.27 because it's overlapping with emission of CO2. So we clearly have CO2 and methane in the coma of Chiron, but we do not see methane ice on the surface. We see more CO2 than in any other object that we have observed, and we don't see CO gas emission, but we see CO ice. Here, clearly, CO2 Gaussian white absorption. It's kind of weird that we see emission of methane and CO2, and we don't see it of CO that is more volatile. And we really think that, one, because methane that is not on the surface is really coming from the subsurface of Chiron, is diluted in water ice, and is being released by a change not in amorphous crystalline because it's really far away. It's called a change in the density of the amorphous water ice. There is a change in density published recently based on laboratory experiments, and it really
You have about
fits
one more minute.
pattern. Okay, so that, sorry, I get excited talking about Chiron. So just to finish, we see methane, but we also see here a lot of products of the oxidation of CO2. And we see here products of the reduction of methane. And we don't see products of the interaction of methane and CO2 irradiated, which tells us that these are in different reservoirs on the surface, okay? Many more to come on Chiron because there is a follow-up paper work done by Won et al. Using DTO observations with wave that is also going to study the coma in detail. So finally, what do we have here? Follow-up observations are going to be really interesting with wave of objects that are observed active because we can really detect different species, and we can study, model them, study the depth, the width, the physical state, if it is diluted, if it is pure, the center of the bands, the asymmetry on the bands. All of that can only be done at this point by James WST, but it's going to tell us so much about the surface and about the activity and about the coma and about the dust, all of that. So that is really interesting to be done as follow-up of observations with surveys. But also, we have very special groups, dynamical groups in our sample. For example, the double dip, that is the most common, and it's also the least spread, the one that shows less differences in spectra. We have one dynamical group that Susan didn't talk about, and that is my question for her. Did you check the detached population in your models? Because all the detached are double dip. It's like the most consistent group. There are no ball type and there are no cliff types. So does this mean that the detached were forming an special intermediate region of the disk? And why the actual models, they don't tell that they are different from the other SIT populations? So it would be good to trace in the models of the formation of the solar system if the detached can come from like a region where there is a bubble on the disk and there is something special that makes all of them double dip. Then here you can see the empty squares. These are the cold classical population. You can see them here. All the cold classical are cliff. But we are already observing groups in the cliff population. The cold classical are different from other cold classical, for other cliff. So this puts us, and you can see also here on the bowl that there are like two different populations. We had 60 objects with JWST, consistent spectra, the most comprehensive and homogeneous sample, but we are already in the small numbers. We need to make more JWST spectra of TNOs, and if we could be directed at some point by photometry, telling us what to observe, that would be great. Because the next step with this disco is to really trace how do these compositional groups behave in the visible and near infrared wavelengths, because we have large surveys there. So we want to have large numbers. We want to see if we can trace these compositional groups with visible and near infrared observation. So
Okay, we need to move on. I'm so sorry. Thank you very much.
This is the last one.
Thank you. Let's thank our speaker. Our next speaker is Joe Lazio, ground-based radar observations of near-Earth asteroids.
Okay, so while the slides are coming up, I'm going to, first off, I have the pleasure and privilege of presenting, but it's really on behalf of a very large team of people. Lance Benner, I think, was originally scheduled to give this presentation, but he couldn't make it, so some aspects of this are on his behalf. And I think this is what, the non-visible wavelengths. So now we're actually going to talk about like 3.5 centimeter wavelengths, things, wavelengths you can actually see. Okay, so why do we want to do radar observations? From a science perspective, I mean, you can see you get shape models. We heard earlier about shape models. You discover binaries. There's a whole bunch of science that comes out of the radar observations by being able to actually target your objects. If you ever want to do a follow-up mission, if you actually want to send a spacecraft to a small body, essentially all of this small, either essentially or all of the missions to asteroids have gone to asteroids for which the orbit has been determined in large part by radar observation. And finally, there's a planetary defense aspect of both the precise orbit determination as well as characterizing the asteroid. Following the collapse, the unfortunate collapse of Arecibo Observatory, NASA essentially runs all of the world's planetary radar infrastructure. So the workhorse is the Goldstone Solar System radar that's attached to the 70-meter antenna in Goldstone. There's also a junior partner, as it were, a 34-meter, an R&D antenna that's also at Goldstone. I'm not going to say too much more about the SHARP project in the Southern Hemisphere that uses the Canberra 70-meter because Shinji is following me. There have been a couple of demonstrations using the Madrid 70-meter and European assets, and there are a couple more that are being planned. So what I'm going to tell you briefly, the current DSN work, I'm going to tell you about what's coming up for the Goldstone Solar System, Goldstone Solar System radar, and then probably going to run out of time, but we'll queue up questions on the future. Okay, so this is actually this is all radar observations. So the different colors, blue is Arecibo, red is Goldstone, green are the recent Southern Hemisphere observations. You can see the dramatic change following the collapse of Arecibo. Roughly the DSN together does something, let's say in round numbers, about 4 dozen objects per year, 4 dozen targets per year. Probably could do more, in fact, could do more, but there are various limitations, some programmatic associated with actually doing more. And here's a collection of recent results, rogues gallery as it were. The upper left may not look like much, but those are the 2021 observations of Apophis. And following those, I mean, it was already pretty clear, I think, or pretty well determined that Apophis is not going to impact in 2029. It's not going to impact in 2038, I think was the next one. This one certainly rules out 2068. And we can actually say now that the orbit of Apophis is nailed down to the extent that it's known to about the scale of this room. 2024 MK, as the name suggests, was a target of opportunity, so it was observed within a month or something. Goldstone, the GSSR, doesn't have a fantastic target of opportunity or rapid response, but there is some capability. So, and particularly in the last few years, it just seems like the number of target of opportunities has been going up. DART, so Goldstone was actually on DART. The Goldstone Solar System radar was within 12 hours, and the initial determination of what had happened The initial estimate of how much the orbit had changed from the Goldstone radar observations was something like half an hour or 33 minutes or something. And of course, that's actually very close to the final result. The key thing here, so this is the horizontal pixels, the bright white pixels that you see, that's Didymos. And then Dimorphos should have been in that Scion box or Scion circle if DART had not impacted. The fact that it's in that green circle is an indication that the orbit was changed, and again, by about something like half an hour or 30, whatever the current number is, 33 minutes, 32. And some of these were Goldstone only, some of them were bistatic between Goldstone and the Green Bank telescope. Okay, so what's coming up? The Goldstone solar system radar is on an antenna that's something like 60 years old. And there are boxes out there that are plausibly older than, sort of maybe half the population of this room. So what's coming up? The DSN is in the process of trying to modernize all of its 70 meters. So the 70 meter in Canberra was completed in 2021, which means actually a substantial amount of the work was done in 2020, which you may remember was a global pandemic, and it was somewhat super heroic to have gotten it completed. Goldstone is now scheduled for 2026, which if you've heard versions of this presentation before, you'll know is a slightly different date. And the original plan was just to do the sort of spacecraft aspects of the 70 meters, but it ended up, it's just way more efficient. Everybody knows that the GSSR has to be modernized, so it's way more efficient to do the radar and the spacecraft aspects together, and that's the decision for Goldstone. I won't walk through the entire thing, but it's almost like it is. Essentially, the interior of the antenna is gutted and completely replaced. About the only thing that's going to remain is the antenna mechanical structure itself. So this is an illustration of what happened in Canberra a few years ago. That if you see, let's see, this structure here is a crane. So if you look out on the skyline of Cape Town, you'll see skyscrapers being constructed. This is that kind of crane. And these cones, two of these cones will be replaced at Goldstone. These cones are something like 2-story buildings. You can see here the amount of material, I actually cropped the figure a bit, but you can see the amount of material that's scattered around the inside of the dish that's associated with this. Here's what happens to like the inside. I mean, there's complete new construction almost. This is equipment, so if you went to Goldstone today, you'd see stuff like this. It looks great, 1960s era or something. This is what you'd see at Canberra. So it actually looks like 21st century electronics. So everybody wants to know what's going to happen. The preliminary design review was accomplished successfully actually during the Planetary Defense Conference. So during the Planetary Defense Conference, I got to stay up till 1 a.m. one night going through the PDR. The CDR is currently, if everything holds, next month. The current schedule then is sort of, let's say in 2 years, the antenna is going to go offline, and you can tell it's going to go offline for essentially 2 years. So there's going to be nothing happening. It's going to be in a birdbath position, no spacecraft tracking, no radar. And this date, I keep reminding everybody associated, this date, Apophis is coming, and we are trying to get, for the first time, there will be a radar track in what the DSN calls its mission event forecast. So this is one of these things the DSN has to be ready to go for this track. Okay, and now, for the future, I said I'd queue it up. I don't know that I have a lot of time. Following the collapse of Arecibo in the US Planetary Science and Astrobiology Decadal Survey, there was a recommendation to conduct a report of what the nation would need for future planetary radar needs. That report has been concluded. This table is kind of my takeaway summary of it, which I can walk you through perhaps offline or in question period. But I think now the question really is one of, does say the US really want to do this? Is there enough interest in doing it? It's not anymore really a technical question. I think we know how to do it. It's a question of, do we have the political will? And I think I'm going to leave it at that if the slides will advance. But I think this is essentially my last slide. The last slide, yeah, this is everything I told you. So I'll take questions.
Thank you, Joseph. Maybe 1 or 2 questions?
So I know a key thing of these observations is that you need a transmitter, right?
Yes.
Can you comment on the possibilities of using SKA and seeing that it doesn't have a transmitter, but it's a massive receiver?
So yeah, so that would be a bistatic. So SKA SK mid could be used as a receiver. The baseline, and I don't remember all of the AA4s and stars and all of that, but in order to, okay, so it could be used for the S-band transmitters, either from the Canberra antennas or from the Madrid antennas. And I guess you have to be thinking about a map of where there's common or mutual visibility. If and when band 5 comes along, which is up at more like X-band to 8 gigahertz frequencies, then the same thing would happen. And that would be a little bit better because the Canberra 70 meter will eventually have a 100 kilowatt capability back. It would be a fantastic receiver, and it's just a matter of getting the mutual visibility between either Madrid or Canberra and the appropriate frequencies.
Just a question about the future, and always because we are in Africa, so is there any plans to have NASA maybe have a radar in Africa? Is there any plans that NASA will have a radar in Africa somewhere? Or that one in Madrid can be enough?
No radar in Africa of which I'm aware.
Okay.
Certainly not from a NASA perspective.
Maybe in connection to what he said, I know that the Space Institute in Ghana has recently converted a 32-meter antenna used for telecommunication for radio observation. This kind of equipment could be used for radar observations. I mean, I know that it would not be useful for emitting, but maybe for receiving.
So, yeah, so that's sort of in the same spirit of the question that Nick just asked. In fact, once upon a time, I should point out, if you don't know, the Heart of Beastock Radio Observatory, which is a 26-meter antenna outside Joburg, is actually an old DSN antenna that NASA transferred to the South African government 50 years ago. So we have looked at, could you use Heart RAO or maybe the Ghana radio antenna with, say, Madrid, and sort of the same question with Canberra. It's a question of mutual visibility, particularly Madrid. You know, Madrid, then Madrid has to point down sort of toward the horizon, and Heart RAO or the Ghana antenna would be pointing toward the horizon. So it's a mutual visibility question of, are there enough objects that could actually be seen in the window where they can both see it?
Okay.
Yeah, Shinji may comment more on this.
Okay, we thank the speaker again.
Our final talk is by Shinji Horiuchi, Southern Hemisphere Asteroid Radar Program, or SHARP.
Hi, hello everyone. I'm Shinji Horiuchi from Canberra Deep Space Communication Complex, which is one of 3 NASA deep space stations, together with Goldstone, Madrid, and Canberra. Yeah. Okay. So why Southern Hemisphere? Because so Goldstone and Arecibo, they've been observing asteroids for decades with radar, but there are some fraction of asteroids which cannot be visible from Northern Hemisphere. So we meant to fill the gap for those asteroids that tend to be missed before. And also, time coverage is also important factor. So together with US radar facilities, some capability from Australia or Asia or Europe are very much beneficial. Yeah. Okay, so here, this is the location of radio telescopes in Australia. So we are part of a long basin array Australian VLBI network. And so our site, NASA site, is located in Tivimbira, which is near Canberra. Sorry, and yeah. Anyway, so we use technique called bistatic radar, which we can only transmit, but we cannot receive that signal because we just use NASA uplink capability. Then downlink is different frequency. So we need other antenna, and we use Australian telescope compact array in Narrabri, and So they have an array of antenna with 6 22-meter antennas. And this is our site. So we have a 70-meter and few different 34-meter. We can use potentially any of these, yeah, when it's available. Okay, and here is an example of observations. We observed 2003 ST220 in 2018. So Goldstone observed first. They obtained nice delayed Doppler image. So this is looks like picture, but horizontal axis is a Doppler spread, and vertical axis is delay. And so we follow the observations around nearest approach around 22nd of December. We don't have a capability to send sharp signal, so we can only monitor Doppler spread. But the variation of Doppler spread is consistent with delayed Doppler Goldstone image. Okay, then we started this project in 2015. At that time, we transmitted at 2 gigahertz. And we used Parkes radio telescope to receive. And since then, we switched to X-band uplink capability radar, and which provided more gains. So, and red part is target of opportunities, and black part are pre-scheduled observations. So up to now, as of last December, we detected 35 near-Earth asteroids. And this year, we've already detected 3 asteroids, so it's now 38 objects. And here is an example of result here. So, okay, and now I want to show some highlights. 2022 RM4 was discovered in late 2022. And this object, Goldstone couldn't observe because by the time it was recognized, it was already flying to south. So these are only radar observations we did, and we have 2 epochs. And we monitor significant Doppler variations, spread variations. And so then from variation of Doppler spread, it can fit nicely with rotation. We derived a rotation period like 16 hours. And this is very elongated object. And more importantly, with these 2 measurements, we could update our orbit significantly. And now we can predict a near-Earth encounter plus minus 500 years. So, and it appears that the previous flyby was nearest, and the second closest was 1734, which was several years after Isaac Newton died. Yeah. And this is very elongated object like this, so with inclination angle 38. And okay, here is another example. We observed this 2023 DZ2 last year. We observed very very large Doppler spread, and Goldstone also observed this one, and they produced nice delayed Doppler images. And this was part of a International Asteroid Warning Campaign observations. So together with our results and with many other optical results and simulations, some of the audience here also participated, and it's been published, led by Lily Etiwal. Yeah. Okay, and this is the latest observations. John mentioned this briefly, but yeah, so we did this 2024 MK was discovered by Atlas Sutherland Telescope here in South Africa, which was the 16th of June. Then we started organizing these observations. So within 2 weeks, it was predicted to fly by. So yeah, we observed as a target of opportunities. And this indicates that at the beginning of the observations, we measure a significant Doppler offset. So in real time, we reported this to John Giannini, our collaborator, to maintain JPL horizon systems. Then during observations, we updated predict, which yields improved signal-to-noise ratio. Yeah. Okay, and also Goldstone did delayed Doppler observations, and next day, using the updated predicts following our result. And we could piggyback the Goldstone observations. So we observed, so Goldstone transmitted with 70 meter, and Canberra TB-Inbira 70 meter we received. So, and we could image as a Goldstone made, yeah. And so this, in fact, this is the first delayed Doppler image produced from Canberra, yeah, Australian facility. All right, and also we try to analyze for different things from Goldstone results, and we image like a polarization ratio. So radar observation is usually producing circular polarization ratios, and so we could image. This is work in progress, but very preliminary results which show something cool. Yeah. All right. Then outlook. So, yeah. So we have, if we have a waveform generator, we can produce as a Goldstone nice delay Doppler images, and also we are trying to simulate at level and computer. So what we would expect for different materials. That kind of things are going on, yeah. And finally, I want to talk about apophis encounters, which will be 29th of April. Oh, sorry, 29 April 13th, so Friday 13th. So Friday flyby, you can remember, yeah. And this one, I want to show. Okay, so this is a view from apophis, view of Earth from apophis. So you see the blue dots are geosynchronized satellites. So it's coming, so you can see Australia here. So yeah, so around the encounter Australia, from Australia we can do radar observations, and you can see Africa. So yeah, so we expect ISK MIT will be operational by 2028. So they can detect our radar echo. And it's flying above Africa and going through Atlantic Ocean and going to US. So yeah, this is the nearest point, yeah. Then going further and further, yeah. So yeah, Goldstone expect to observe from this from a few weeks ago before encounter, but yeah, there will be massive campaign to observe this, yeah. So I stop here, yeah.
Thank you, Shinji. Maybe one quick question.
So from your last slide, it appears that SK Mid is technically able to, receive signal, but are you guys in conversation with people at SKA?
Yeah, that's why I'm here. I'm trying to approach someone, yeah. And also good thing with SKA, so it can form subarray, so that means there are a few different antenna. It's equivalent, so SK will be equivalent to a few different antenna. So they can do kind of interferometry, and so that we expect to determine the spin axis precisely of asteroids. Yeah.
Okay, so we thank the speaker again.
And don't forget, we have a poster session starting now until 3:30, when we resume.
Yes, we will resume in 30 minutes. There are still one or two people that have not uploaded their slides, so please come to the tech desk. I really enjoyed it too. That was very interesting.
Thank you. I really enjoyed virtual.
The stellar flyby, I mean, I'm not familiar with these models and the sort of ideas why the solar system looks like it does. Is the stellar flyby sort of a new idea, or is that something that?
It is new and old.
It's old, but no one's been able to do it quite like you've shown.
No, but basically it was an add-on to the NIS model.
Yeah.
All the others.
Yeah.
And basically, you get all that already.
You don't need the NIS model.
You don't need it. I mean, yeah, there will be some
And
kicked out, but it's not the main course.
and does the model even predict sort of what?
Definitely wants to talk to Anne. I have a cheat sheet for final comments.
Mhm.
So my plan was.
Do you want to do the closing?
Yeah, but I'm going to ask you. So my plan was like to say, okay, as a wrap up, like here's here are all the things we've heard about. We've heard from LSST how many more things we're going to get. We've heard about these different facilities. We've heard about the brokers. We've heard about the different wavelengths, the characterizations, and like it's a pretty exciting time because we've got all this stuff coming online, and we clearly are trying to kind of make connections here that are global to do all this stuff. So on my list then is to talk about the PDC that people should be aware of. You and Jill doing whatever social.
I'll do that right at the end. So.
And then thanking everybody. I think that's it.
There was one, the proceedings.
The proceedings. That's on my list too.
Okay.
Yep.
Cool. So if you don't mind doing that,
I'll do
great.
it. I'll do it. Yeah.
Not now.
Not now. Wonderful. Is your talk loaded?
Yes, yes.
Perfect. That's great. It's so good to see you here.
It will be here.
It will be here 4:40.
Okay.
Yes, thank you. Thank you. She's our final speaker. So we should be starting in about 20 seconds here. Our first talk is online. This is the active bodies session, the very last session of the FM3 small bodies in the solar system focus meeting.
What now?
Starting.
Okay, we are starting. So for those of you in the room who are not ready for us to start, get ready for us to start. The first talk is by Henry Shea. It is Rapid Detection and Characterization of Active Small Solar System Bodies in the LSST Era. Order in the court, please. Go right ahead, Henry.
Thanks, Andy. Can you hear me?
Yes, we can hear you.
Great. Yeah, thanks for the introduction, and thanks to Nick and Amanda for the opportunity to speak to you all today. So yeah, my name is Henry Shea, and I'm going to be talking about basically studying comets in the LSST era. We've heard a lot about LSST already, so I'm not going to bore you with all the details again. I'll just point out that I'll just highlight a couple things that, just to remind you, the survey will produce about 20 terabytes of data per night. So it's quite a bit of data. But hopefully, this is expected to really benefit sample size limited science, of which there are many such cases in the general area of active bodies. So that's good for us. I'll also point out, given the international audience here today, that I'll remind you that all transient alerts will be world public immediately, and I will specify that all solar system detections are considered transients. And so all solar system data will essentially be, or at least the catalog data will be public immediately. And so even if you don't have data rights, this is still something you can be involved with. So just something to keep in mind. And again, the survey is expected to start late 2025. So so in about a year plus. So I'll just run down really quickly some opportunities in the area of active body science as I see them in the LSST era. So first is the opportunity to discover more rare types of active objects, such as main belt comets, active centaurs, asteroid disruption events, things like that. Also discovery of new types of active objects. So things, maybe we'll discover some, Jovian Trojans that are active, or more active NEOs, something like Bennu, which is famously thought to be inactive, but turned out to be active. We'll hopefully better trace the ice inventory of the solar system. LSST should generate a really great systematic long-term monitoring catalog of a large sample of comets, which will be useful for a lot of different science cases. Hopefully we'll increase our detections and therefore knowledge of cometary outbursts. And also just bright comets are really great outreach subjects. So it's something we don't always talk about, when we're talking about our science. But here's just an image of an outreach event that was in Hawaii to see Pan-STARRS's first comet, P2011 L4, which was visible right at twilight. So I got a really good crowd there at sunset. And here's a picture somebody took from New Mexico over city lights, in twilight in a cloudy sky. So, comets are cool. Cool to us, also cool to regular people. So, there will be a lot of challenges in the LSST era. So three that I just want to highlight is the big one is we need efficient and effective methods for detection and confirmation of activity and outbursts in large data sets, or the large data set, the LSST data set. And then the other challenges are we need to make the best use of limited resources for follow-up observations, as we've sort of heard already in this meeting. And we also need to have effective community coordination and information dissemination. And of course, the last two are sort of intertwined with each other a little bit. So I will sum up my talk right now. So spoiler alert, we're not ready. yet, but if the slides will advance, but we're working on it. So, I'll touch on first activity and outburst detection. So I could give a whole talk about this, so I won't talk too much about it, but suffice to say there are many different ways that people have devised to look up or to detect activity. And you can read about many of them in this white paper here that we wrote about 5 years ago now. So I will point out only that some algorithms will require catalog data, so numbers basically, which are much easier to work with, while others will require actual image pixels basically. So this will impact the analysis speed and therefore the computational needs needed to run those analyses. Another just spoiler alert for activity confirmation, we'll probably rely mostly on the survey itself to do self follow-up of any comet candidates, just because the paradigm of using follow-up facilities to confirm activity probably won't be feasible in an LSST era when we have so many other needs for the follow-up facilities. But we will need some sort of system to track the confirmation statuses of various candidates. So that's something to keep in mind. This is just a figure showing how comet outbursts are found or can be found. So basically just doing long-term light curves. This is just to illustrate there is a way, or there is a systematic way that people have for detecting outbursts. And we just need to scale this in the LSST era. So within the LSST Solar System Science Collaboration, we've done some thinking about what kind of infrastructure or what kind of elements in the community we need to get from LSST observations to science. So we came up with this flow chart here. So it's pretty busy, but I'll just highlight the key areas. So LSST is over here. I think you can see my cursor. Then you'll get a alert stream that will go to the alert brokers, which we heard about yesterday. And then these alert brokers will filter out will send out their information to groups like the solar system user community, essentially, and also observation facilities, and maybe have some sort of observation coordination website. The community will publish publications, and some of these will be kind of discovery announcements, short form announcements, and these will filter back into the observation coordination websites as as the needs arise. So so it's a pretty busy chart here, but there's some things that exist and some things that do not exist. So I'm just going to highlight a couple elements of this flow chart. So the first is the alert brokers. So luckily, we heard about a lot of these, or we heard about 2 of these yesterday, so I don't have to explain too much about it. Basically, the goal of the alert brokers is to ingest the LSST alert stream, extract solar system alerts, and then generate a value-added alert stream, basically adding higher order data products to the alerts and then redistribute it to the community. So things like, if objects have known colors or light curves, things like that. So we heard about Lazar and Adler from Colin Snodgrass yesterday, and we also heard about snaps from David Trilling. So if you want to know more about them, those brokers, you can talk to either of them. Also, there's this pipeline that's being developed as an in-kind contribution from Italy called Adacted. It's being led by Laura Eno in Italy. So just to highlight the aspects of the alert brokers that are relevant to active bodies. So Adler will have activity detection and characterization capability, as Colin discussed yesterday. So some of this will be developed, is being developed in-house. And also there's some possibility of Adacted running on Adler and providing sort of more advanced or just different capabilities. Snaps, as David mentioned 2 days ago, sorry. is focused at the moment on inactive objects, but it could deal with active objects in the future. And then finally, adapted is actually specific to active objects. So it will have, right now it's still being developed and requirements being specified. So it should have some other advanced activity detection algorithms to be determined, and also do advanced activity characterization. So things like calculating AFRO, tail angles and lengths, things like that. And so it's being developed, or will, probably is being planned as a software package or pipeline that may be available via Adler or also the Rubin science platform. So coming back to this flowchart, I want to focus on this part over here now. So rapid short form announcements. So this is another in-kind contribution effort being led from Canada. The leads are Laura Buchanan and Wes Fraser at NRC. And this is a new publication service that's being developed that aims to provide a venue for short form announcements about discoveries aimed at facilitating follow-up observations. So for those of you familiar with CBETs or ATELs, this is similar, but it's aims to address the current needs of the small bodies community, which those don't do at the moment. While this is being developed as part of the LSST collaboration, it's intended to be open to the entire small bodies community. And planned features include things like machine readable sections to interface automatically with follow-up observation tools and facilities, and also auto generation of forum posts on the LSST community forum to encourage discussion and collaboration among community members. So that's what's going on there. And lastly, I will talk about this part. So follow-up observation coordination is something, we've heard a lot about follow-up observations, but not necessarily about how we'll coordinate them across our entire large international community. So the aim of this is to match observing needs to appropriate observing resources, minimize duplication of effort / duplication of observations on precious follow-up facilities, and also automate links with the other ecosystem elements where possible. So, of course, we've seen a lot of talks and posters about this session, particularly the one by Colin this morning. So this is a general discussion, not just limited to active objects. There's also a website being developed by Carrie Holt and Tim Lister at Las Cumbres Observatory, which will kind of meet is being designed to meet the requirements that we've kind of laid out. We want this website to serve. So this is being developed within the LSST collaboration, but intended to be open to anyone. So if you're interested in helping to define those requirements, you can talk to either them or me afterwards. So I will that was kind of a whirlwind tour through this thing. So there are a lot of elements and people are working on them, but they are currently under construction. So, as I said, we have like a year plus to go. So hopefully we'll make good progress on all of these between now and then. So because this is active object, this session is active object specific in this talk as well. I just wanted to talk briefly about special challenges for active objects. So something that's not unique to just active object cases or a couple other cases, but there are asteroid disruption and comet outburst events can have very short time scales. So on the scale of days, so require rapid identification and follow-up. So needs very fast turnaround. Some active objects may look like false detection. These are real things that look like artifacts. So any algorithms that are designed to detect false detections can't be too aggressive. So just as an example, this is a series of images from Pan-STARRS of 331P Gibbs. For those of you who don't know that designation, that's a disrupted asteroid that was discovered or observed by Pan-STARRS 4 months before it was actually discovered by Alex Gibbs at the Catalina Sky Survey. So, it doesn't look like a point source. our pipeline did not pick it up. But obviously, if we looked at it, we'd see, hey, maybe this is something interesting, but lessons learned. Also, on the flip side, there are artifacts that look like real objects, especially to activity detection algorithms. So while the false detection algorithms can't be too aggressive, they still need to be pretty good. Otherwise, the candidate list will just be too long for humans to manually go through. So just as another series of examples from Pan-STARRS, none of this activity is real. This is an image artifact. This is not a picture of like 10 comets in the same field. This is a glare or a reflection from a bright star. And the thing with the arrow is also part of that glare, but it wouldn't be obvious if you didn't see them again and again. Again, this is like some kind of readout problem, and just who knows what's going on with these. So these are all picked up by our comet detection algorithms, so and had to be thrown out. So so this is thank you. I think I have 5 minutes. Okay, so
two minutes until we want to have questions. So
okay, perfect. I think I'm almost done. So I'll just point out that human vetting of all active object candidates is likely to be needed for the foreseeable future. And then I would point out that this is part of the active object detection workflow, and is also part of what needs to keep pace with the LSST data rate. So just to show you very quickly, this is sort of a page that's generated by Pan-STARRS every night. So of all the objects that were flagged as comets, so there's a lot of garbage at the beginning. So if you can kind of see the scroll bar here, so you can see how long this page is. And then you kind of have to scroll down to here before you start getting real objects or possibly real comets. So, and this is just for Pan-STARRS, so you can kind of imagine what LSST will be like. So something like that we have to watch out for. So I just said this, so human vetting needs to be taken into account. Most activity detection methods have not been tested to see if they can keep up. Active objects are also not currently being well addressed in LSST preparations, but there are good reasons for this because point source data is more relevant to larger group of people, but it is something we have to watch out for. And to be honest, false detection assessment and development of mitigation, in my view, may not be possible or practical until LSST camera data actually becomes available. So, so here's my last slide, my summary. So just numerous efforts are being carried out worldwide to address various elements of the solar system follow-up ecosystem. Many of the elements of this ecosystem and the challenges apply to all solar system body science, but active objects also have like an added set of complications for that. And I'll finish off by mentioning that preparation for solar system science is being carried out by the Solar System Science Collaboration. You can see the website here. And I'll put them on the spot that if you want to find out more, you can talk to Colin, Serial, or Siegfried. I'm assuming they're somewhere in the room in person. If you want to get more information, they'll help point you in the right direction. So with that, I will thank you all and take questions. Thanks.
Thank you, Henry. Any questions? I can start with one. Amanda Sikafus, Planetary Science Institute. I don't think I saw the numbers, although you alluded to this. We've been seeing, here's how many current objects there are that are MBAs or NEAs or comets, and here's how many we think we're going to have with LSST. Do you have an idea of maybe a nightly basis, how many false detections and how many real active things we might be seeing eventually?
I do not. The canonical thing you keep hearing is everything is going to increase by the order of magnitude. I think active objects will actually increase probably by more than that, just because, as we know, like things increase as they get fainter. So, so if we become more sensitive to fainter activity, the number of active objects we might find could very well like explode. I don't have a good number for you except for that very generic order of magnitude increase in everything. I do not know the nightly count of solar system objects though. Sorry about that.
Nope, that's fine. Thank you. Anybody else with a quick question?
Hi, Andrew, Nick here. So you showed the problem about all these artifacts that appear like potentially active objects, but you can discard 99% of them, right, if they're not moving?
Those objects were moving. Well, this is partly due to the Pan-STARRS cadence, I think, where these things did happen to line up in a way that was not immediately rejected by the pipeline. So these were moving objects that were additionally flagged as being active. So yeah, so it's possible that the LSST cadence won't flag these as things that are on reasonable looking orbits. But as I said, I think that remains to be seen once we actually know what kinds of artifacts are present in the LSST, the real LSST data.
Thank you very much. We're on to the next speaker. The rest of the speakers for this session are all going to be in person, and we're just going to remind you, you'll see a timer in the front. It starts at 10 minutes. So by the time you see a 3 on that timer, that's when we normally would be cutting you off for questions.
Right. Okay. And our next speaker is Gonzalo Tancredi, who will be speaking about transitional objects among asteroids and comets monitored through archival images from large surveys.
Okay, good afternoon. This presentation is part of the thesis of master student Sibla Martino, and it's a collaboration with colleagues from the Observatorio Nacional de Rio de Janeiro, Brazil, and with Javier Licandro from Spain. What we say is transitional objects are those objects that share some characteristics with asteroids or with comets. In particular, we are talking about asteroids in cometary orbits are those objects that behave dynamically like comets, but have not shown any kind of comet activity. And the active asteroids that have a typical asteroidal orbit, but have shown some kind of activity like dust dissection at some point. And the motivation of this work is to determine if the asteroids in cometary orbits, ACOs, are dormant or extinct comets, or asteroids escaped from the main belt into cometary orbits, and determine also the period of activity on inactivity of active asteroids. Nowadays, you know that we have a little more of over 1 million asteroids, and almost 1 million with precise orbits. And if we use the usual T7 less than 3 criteria for distinguish between asteroids and comets, we will end with something like 17,000 asteroids with T less than 3. But as we know from dynamical studies, this is not enough to have an object with unstable dynamics like the typical cometary ones. So that's what we have developed another criteria in 2014, and it's the one in the upper right table, where at the end, what we can say is that it's only on the order of 700 objects, asteroids, with cometary orbits, with really unstable and typical kind of cometary orbits. And to have another number, there is on the order of 770 comets discovered up to a few months ago, and almost 600 of them are from the Jupiter family. So what we have done is to use archival images, either from the IAC telescope, the Instituto de Astrofísica Canaria telescope, the ESO-BLT, and the Dark Energy Survey. And also some new observations with the Impacton telescope in the north part of Brazil. For the data reaction, well, it's the kind of things that Henry has already mentioned. In one sense, what we compute is the surface brightness profiles, where you compare the surface brightness profiles of asteroids with those of field stars. So if we see a widened profile, then it's an indication of activity. And also the reduced magnitude. The reduced magnitude is the magnitude taken at a electronic distance of 1, geotechnic distance of 1, and phase angle 0. this magnitude should not be dependent of the heliocentric distance, but if we observe that there is a variation of this magnitude at different heliocentric distance, this could be an indication also of activity. For example, these are a surface brightness profile of 3 different objects. One with inactive, where you can see with a green dots that it's almost similar to the profile of stars, field stars. In the middle, it's let's go to the one in the right. In the right, we have a very active object where you can see that there is a departure from the green dots to the blue dots that correspond to the stars. And in the middle, we have something like it's a little bit in between. I mean, it's maybe an object that is possibly active. There is a little discrepancy between the profile of the stars and the asteroid. The other, well, these are, for example, the objects that we have detected with candidates of activity. These are 9, but we have a little more. Some of them has real indication of activity. Some other are more to be discussed. And the other thing is to use this reduced magnitude. This is the reduced magnitude as a function of heliocentric distance. As I said before, if the object is inactive, then the reduced magnitude should be almost constant. There is only some variation due to the rotation of the asteroid, of the amplitude of the rotation of the light curve. But in the right plot, it's for 133p, you can see that there are some points, those close to the perihelion, the left line is the perihelion, the right line is the aphelion. There are some points close to perihelion where the reduced magnitude is quite bright. That means this object is active. The symbols correspond, for example, to observation before and after perihelion, and we include observation from larger base. Any data from the MPC, what we have done is to download all the data from the MPC and some of our own data. And for example, these are several candidates of activity based on this. What we have to confirm for this activity is that the observations are done possibly by most of one observer and in different days, because as it was already mentioned by Henry, there are a lot of artifacts and there are a lot of bad reports where if you have just one point, it's not enough to confirm activity. So coming to the conclusions, we have increased the sample because we have a previous paper, and now we have analyzed it on the order of 160 asteroids in cometary orbits. This is something like 23% of the total known of the 700 asteroid in cometary orbits. Most of them are ACO. But among these, only 11 of them have presented some kind of low-level activity. None of them has presented a very clear activity. So what would say is something like a preliminary conclusion is that we could rule out a smooth continuum for an active to inert objects. That's something that has been discussed from a long time ago. There might be some kind of smooth decreasing of activity, but if there is some kind of smoothing decreasing of activity, we should see more low activity, but it's only a very small percent. Within the population of ACOs in Jupiter family orbits, there could be a majority fraction of escaped asteroids with a few cases of dormant comets. So we are thinking now that maybe they are bona fide asteroids and they have escaped from some dynamical routes into a cometary orbit, and they are not dormant comets as we thought at the beginning when we start these things. Nevertheless, I say that further dynamical studies are necessary to understand the dynamical routes from the asteroid belt to the unstable cometary region. Regarding the active asteroids, we studied 7 active asteroids. 4 of them show activity in the images. In the case of this object, we extended the activity period for 3 weeks. And the conclusion is that the activity episodes are restricted in time and not always occur in the same region. For example, not always occur in the same perihelion passages. This question, from our point of view,
put some questions about the hypothesis of sublimation of some objects, because the sublimation as the activity mechanism, because if we, the object should be observable with activity at the same places in different passes. So the number of active asteroids is still very low. This is something like, I think, or 30% of the known active asteroids, but as I said before, the activity is very restricted in time. So that's all. That's, well, the previous paper that I mentioned before, it's the one that was published in 2019. It includes less objects, the paper about the criterion, and we are submitting a new paper with these observations to ANA soon. Okay.
Thank you very much. And do we have one quick question, maybe? No. Okay. Well, we can. Quick one.
Thanks, Taquino. So, you said that there was actually. How certain are you of the discreteness between comets and asteroids? In short, you saw some low-level activity. Could that be? What would you expect for like LSST type numbers?
When we start this work, we expected that of this 700 of asteroids in real cometary orbit, that we would expect a large fraction, maybe several 10%. But as you see, we only observe maybe less than 10% of with activity. So that's the conclusion, that this smooth transition should not occur. I mean, it should be something like, or it is sharp when it was active and then suddenly it stopped activity, or the other possibility is that they are not comets at all. They are not dormant comets, they are asteroids escaping from the main belt. And dynamical studies show that there is a low probability path from the main belt to the unstable. Because, for example, if you enter into a resonance, then you get into the border of the resonance, and then you can escape, and then you can start having encounters with Jupiter that makes the dynamics unstable.
Thank you very much. And I'm sorry, I misread the schedule. We do have more online talks.
And the next online talk is going to be given by Ian Wong, who will be speaking about follow-up studies of active solar system objects in the LSST era.
All right, thank you. Can you all hear me?
Yes, we do. At least I do. I can't speak to anyone else.
All right, thanks. So Henry gave a really good overview of the methods that people are using to try and detect active solar system objects within LSST data. So in this talk, I'll be talking about a particular type of follow-up characterization study that is enabled by our favorite space-based observatory, which is, of course, JWST. So just an overview for people who may not be intimately familiar, James Webb is a specialist in near-infrared and mid-infrared observations. So between 1 and 5 microns, there are 3 instruments. Of particular note is NIRCam, which is the imaging instrument and has the highest spatial resolution. Meanwhile, NIRSpec is the spectrographic counterpart and has various spectral resolutions available. At longer wavelengths, you have MIRI, which is a mid-infrared instrument that has both imaging and spectroscopic capabilities from 5 to about 30 microns. So of particular note for the active object community is the availability of integral field units on both NIRSpec and MIRI. So in short, these IFUs break up the field of view into essentially a series of slits, which are then dispersed onto the detector. And the post-facto data processing reconstitutes these slits into a data cube, wherein every single pixel has the full spectrum of the instrument. So this is really useful for characterizing the composition of coma, as well as looking at spatial distribution of the coma itself. So for NIRSpec, there is the IFU, which has a 3x3 arcsecond field of view. And there are 3 spectral resolution settings that are available. We have prism mode, which is R of 100, all the way down to the high resolution ratings, which are of about 2700. In the mid-infrared, we have MIRI, which has the medium resolution spectroscopy mode, has a fixed spectral resolution ranging from about 1500 to 3500. And there are 4 channels spanning 5 to about 28 microns. All 4 channels can be observed simultaneously. However, within each channel, they're split up into subbands. So to stitch together the full spectrum, you need to observe 3 epochs and the 3 different subband settings. So how do you get follow-up opportunities with J2ST? So the first possibility is to do a DDT. These are proposals that are accepted throughout the cycle. It cannot be a simple resubmission of a unaccepted GEO proposal. You can duplicate targets that have already been observed, but the duplication has to be justified and well-motivated. The DDT, the benefit of that is that it has accelerated review of roughly 2 to 3 weeks. And there's, of course, funding available once the DDT is approved and the first observations are attained. We also have TOO, Targeted Opportunity Programs. So those proposals are accepted alongside the regular GEO proposals, which are due in October. You can have unspecified targets, multiple such targets if you want. And you can also specify the level of disruption. You can have disruptive or ultra disruptive, depending on the criticality of your observations. What's notable is now we have multi-cycle TOOs, so you can apply to have a TOO that's active for 2 or 3 cycles, and the funding will roll in once the TOO is triggered. So I would like to present an example of a DDT. This is an observation of Chiron, the first centaur discovered. So Chiron, in brief, the orbit spans the region between Saturn and Uranus, and it's the second largest centaur with a mean diameter of about 210 kilometers. It's also one of the most well-studied centaurs, and it's notable particularly for its activity history. It's been detected to be active many times during its observational baseline, and most recently in 2021, shortly after aphelion at 18.8 AU, there was this detection of another outburst, mostly with ground-based photometry. So Chiron was actually included in the GTO Cycle 1 program. Unbeknownst to the designers at the time, it was going to be active when it was observed in 2023. There's a paper by Noemi Pini-Alonso summarizing the findings from that observation. So looking at that spectrum, we were motivated to get a DDT to follow up the characterization of the coma using a higher spectral resolution mode. And running out of time here, but here's the spectrum in full. The DDT spectrum, we have beautiful CO2 ice absorptions, as well as organics. But of course, for all the active object folks, the most interesting parts are the emission of CH4 and CO2. So the CH4 and CO2 is notable because the CH4 is the first detection of methane outgassing on a centaur. And what's notable is that there's also no evidence for CO, which has otherwise been pointed out as the leading candidate for activity on these distant objects. So the high resolution mode of NIRSpec IFU allows us to separate out the lines very cleanly from the continuum and do some spectral modeling to get the abundances. So CH4 is dominant outgassing species. There's a rate listed there. The CO2 is about an order of magnitude less in the production rate. And the true power of the IFU is that we get spatial information for free. So this allows us to simultaneously do coma mapping across the entire field of view, and we get these 2 very distinctly spatially confined coma for CH4 and CO2, suggesting different production regions and perhaps different mechanisms of production.
I have about a minute before you eat into the questions, and there you go.
Yeah, I would just like to summarize that this J2ST is open for business, and the community is encouraged to submit these TOO and DDTs for objects of their personal interest. And as LSD comes online, there's going to be a flood of these active objects, outburst detections, disrupted asteroids. So I just would like to let the community know that these opportunities are available, and we encourage you to choose targets that interest you and propose for these opportunities. So thank you.
Thank you. Questions for Ian?
Hi, Ian. Nick here. Can you go to your second last slide, or were you showing the next one? Sorry, so the last one. Was this done with the IFU?
Yes.
So do you have spatial information as well? Did you see any changes in the coma? You know, different elements at different parts of the coma?
Well, oh, you mean variations? So the profiles of the outgassing look relatively similar at each pixel. Of course, the production, the amount, the saliency of the bands varies. So the color shading here shows the essentially the column density of those species. But you don't see any, for example, the rotational temperature doesn't change appreciably. Yeah.
Any other questions? All right, thank you very much. We'll move on to the next speaker.
All right, the next speaker is Kay Aravind. He will be speaking about unveiling cometary composition, importance of spectroscopic follow-up in the era of large discovery surveys. And I'll give you a heads up when you've got 2 minutes left.
So good evening, everyone. Today, as my topic says, I'll be talking about the importance of spectroscopic surveys in the upcoming era of large discovery surveys of comets. And specifically, I'll be talking about optical spectroscopy. So this crowd doesn't need an introduction to comets because you are all experts in this field. So these primitive primordial bodies which were formed using the ices from our protosolar nebula, they sublimate as they reach the sun, and this provides us with an opportunity to study using different observational tools the composition of these bodies and how they vary as they move across the orbit. And when I say different observational tools, I'll be talking about optical spectroscopy and narrowband photometry. So this is how a typical optical spectrum of a comet looks like, where you have plethora of emissions from CN, C2, C3, NH2, etc. And you have defined set of filters which are defined for the various emissions occurring in comets, and you get images corresponding to each filters. Yeah, both these techniques have their own pros and cons. Since I'm a spectroscopy person, I will be starting with the advantage of spectroscopy. It provides a complete picture of the emissions occurring in the optical regime, and if you have a long slit, it provides an opportunity to cover the spatial variation of emissions in the spatial axis. But in the case of narrowband photometry, it is limited to the available filters, and also you don't have the spatial information. But on the other hand, for optical spectroscopy, it always demands a large telescope time, and it is more prone to observational errors or mishaps. But on the other hand, narrowband photometry can be efficiently done from smaller telescopes too, and it provides a better coverage in observation, like the TRAPPIST has been doing for a long time. And it can also be used for computing the rotational periods and analyzing coma morphologies. So here I present a few transmission profiles of narrowband and broadband filters over an optical spectrum. So as you can see here, broadband filters are not very efficient in studying the activity of comets, because most of the transmission profiles are contained with a blend of many emissions from strong molecular bands. But if you want to study the activity of a comet using photometry, narrowband photometry is the to-go method, because you have dedicated filters which can look at to the particular bands. Despite the differences in the observational methods, reduction method, analysis method, we were able to showcase that we can use spectroscopy as a complementary study for activity trends in comets, where the open circles are observations from TRAPPIST for 46P Vutanen, which was published by Molan et al. And the closed circles, the solid circles, are from our spectroscopic studies. And we were able to show that the activity we obtained from two different methods are very much in complementary nature. And we were able to show with comparisons with the previous apparition data that the comet 46P had a very truly high homogeneous nucleus. And sometimes spectroscopy can be beneficial in the case of comets which are very dusty, because in narrowband photometry you have to scale the flux within the dust continuum and then subtract it from the gas filters. But in the case of photometry, it is spectroscopy, it is more a visual fitting, where you fit a solar analog spectrum to the continuum and then subtract it to get a pure gas spectra, and you will be able to get clean spectra even if the comet is at a very large heliocentric distance. And then we can again compare with the narrowband trends, and also sometimes add to the trends to have a very large coverage of about 700 days or something. And as I said, if you have a long slit, then you have the benefit of comparing the emissions occurring in the photocenter and also exploring the variation of emissions in the spatial axis. Sometimes if you are lucky enough, then the ion tail or the projection of an ion tail coincides with the slit, and then you will be able to look into the ionic emissions which are occurring at different wavelengths. So these ionic emissions are very important to study because they are emissions from the primary volatiles present in the comets. And if you move into higher resolution in optical spectrum, then you will be able to see that the emissions which are seen to be very much blended in the low resolution get splitted up into their own rotational and vibrational emissions. And here is an example of the CN band, where you can see that the strength also keeps varying as the comet moves around its orbit. So if you keep monitoring the comet in high resolution, you will be able to study the physical conditions of the comet at the time of observation as the comet was moving around in its orbit. And if you are again lucky that the geocentric distance was high enough that the Doppler effect comes into play, and it helps in splitting the forbidden oxygen line and the cometary oxygen and the telluric oxygen. So you will be able to study the variation of this green to red doublet ratio as a function of the radial distance from the photocenter, and we will be able to fit models to understand whether it is a H2O dominated comet or a carbon dioxide dominated comet. There are various literature which talks about it. The thing to emphasize here is that this observation was carried out during using a 30,000 resolution. So even with such medium resolutions, we will be able to carry out green to red doublet computations if the geocentric velocity is high enough. So there exist many surveys as of now which have been discovering comets for a very long time. I have listed a few of them, and the upcoming era, the LSST era, will be discovering a large number of comets, and they'll be single-handedly discovering thousands of comets. New interstellar comets will be discovered, and the beginning of activity of comets will be flagged from a very large heliocentric distance. So one thing to keep in mind that if, in this era of big data, we have to keep in mind that all comets are not similar. They don't have the similar composition. Some comets might behave very differently. So it is very necessary to have a preliminary analysis with a spectra to confirm the general emission characteristics of a comet, and also systematic follow-up using optical spectroscopic observation, and also other NIR or UV spectrum is very necessary to monitor the changes in the activity, and also to know whether something is popping out or something is diminishing as the comet is moving in its orbit. And as I said, interstellar comets will be discovered. So it is important to look at the low resolution spectra of interstellar comets as and when it is detected, to see if it has resemblance with the existing solar system comets, like what it happened with the first interstellar comet 2I Borisov. So we were able to, while the entire world was looking at the comet using big guns like 8-meter and 10-meter telescope, we were able to use a 2-meter telescope to observe the comet spectroscopically, pre-perihelion and post-perihelion, to report a possible heterogeneous nucleus of the comet. Since I said high resolution spectroscopy, only a very few comets have been observed in high resolution to detect the G/R ratio. So if we look at the existing data set, there seems to exist some sort of visual trend, and there seems to be an offset in the observed first interstellar comet's G/R ratio. So in this era where the LSST will be detecting activities from very large distance, it will be very good to use observations from the VLTs and ELTs to compute the G/R ratio of comets from very large distance all the way up to its perihelion, etc. And if we get to do this for comets like interstellar comets, it will be very good to understand the photochemistry happening in these primitive materials which were born in some other solar system. To summarize, we all know comets are primordial remnants of a solar system, so it is necessary to characterize all observable comets. Even though photometric surveys are the best way to increase number of detection, spectroscopy holds the key to unveiling the primary composition of these bodies. And also, as many talks in the previous session also showcased, dedicated spectroscopic follow-up of newly discovered comets, because comets are very unpredictable bodies. It is necessary to spectroscopically follow up as they move into the inner solar system. And most importantly, a maintained database of the past, present and future observation, both spectroscopy and photometry of comets, is very necessary to have a large-scale analysis of the distribution of these bodies in the solar system. Thank you.
Thank you very much. We have questions. Back to Mitch.
Sorry, Nick again. You didn't mention which telescopes you're using to do
The
these
Indian, all of them were from Indian telescope. We use the 2-meter HCT Hanley. Then we have our own telescopes, 1.2 and a newly installed 2.5 meter in our Physical Research Laboratory Institute.
Excellent. Anyone else? Let's thank our speaker again, and we'll move forward. Thank you.
The next talk, Near Jupiter Comets, Activity and Characterization in the Rubin/LSST Era. Talk to be given by Theodore Roosevelt Coretta.
It's Richard, but thank you. So hi, everyone. Thanks again for letting me give this talk, and thanks to the organizers and the moderators. I want to get you all excited and interested about the possibilities to study comets that get really, really close to Jupiter, in the next decade and a half. And that doesn't just mean the impactors, like you can see the evidence of Shoemaker-Levy 9's impact into Jupiter on screen, but also the temporary captures and the co-orbitals. This is a really rapidly evolving population. This one particular object that you can see in the plot on the top, this is the evolution of the orbit of P 2019 LD2 from 1925 to 2100. And in that period, it had 4 completely different orbits because it keeps undergoing really, really rapid, really, really significant deep encounters with Jupiter. This might be dynamically interesting, but one of the reasons that it's physically interesting is that, just interior to Jupiter is when comets start to vigorously sublimate water ice. So these rapid dynamical changes can result in rapid thermophysical changes to the state of the nucleus. And it's kind of like you're trying to cook dinner, but you're constantly changing what heat you're cooking at. It's hard to really know what to expect from these objects. They don't really have, a stable orbit and a stable thermophysical state. Things change rapidly in this region. If you don't care about thermophysical properties so much, another reason you might care about the properties and activity states of comets that get really close to Jupiter is that these are the primary impactors in the Jovian system. A really, really ice-rich outer solar system Centaur and a somewhat, devolatilized Jupiter family comet are going to impact the moons, the Galileans, at different rates. They're going to have different properties. And it's hard to know exactly whether or not these would be really different or kind of insignificant, but interesting. One of the things you can see on the left-hand side here are examples of what people call catenae. These are crater chains on the moons of the Galileans, or I should say on the Galilean moons, caused by comets that have broken up like Shoemaker-Levy 9, and instead of hitting Jupiter, have ended up hitting the surfaces of these moons. We want to understand not just how comets are evolving in this area, but what that information might be able to get us about, how to date the moons, how to understand how comets are breaking up in this region. So I know that seems really exciting, but there aren't that many near Jupiter comets that have been yet recognized. And I think this is going to be the thing that's going to really change. There's 2 temporary co-orbitals. That's what I'm going to be talking about mostly in this talk. There's been multiple temporary captures and of course impactors as well. Even if I'm only listing Shoemaker-Levy 9 on this slide, think about all the times you've heard in the news or read papers about impact flashes on Jupiter. Those are all near Jupiter comets that were below current survey limits, or near Jupiter, objects. Maybe they were temporary captures beforehand. And it's hard to tell these dynamical classes apart from each other because orbits can evolve so quickly here. For an object that might be in a temporary captured state, given about 10 years, it's really kind of impossible to trace its orbit back precisely and know what kind of population it came from ahead of time. We're going to be finding objects, but we're not really going to know exactly all of the steps that happened to them that created their modern activity, their modern properties. So the question for this talk is more or less, can we sort out this mess? Can you sort out all the complicated dynamics that evolve really rapidly from the pretty significant thermophysical changes that can happen associated with those dynamics? The punchline here is that, we're going to be observing and finding lots and lots of objects that are interesting dynamically, but, they're going to be extremely faint. And how do we ask all those same questions in the Rubin era when the typical discoveries are a lot fainter than the modern ones? But you guys have been hearing about that for the past little while. So the case study I want to talk to you all about today is 2019 LD2, the object from that first text slide, and P 2023 V6, which is the second and most recently discovered Jupiter co-orbital. We wanted to try to understand how important all of this mess was. So we observed these two Jupiter co-orbitals at more or less the same heliocentric distance, the same true anomaly, the same phase angle. We'd expect that given these two objects and their recent dynamical evolution, they would be within a few Kelvin of each other. So the big picture question we're asking of these two objects is, given the same inputs, do they behave similarly? We also think they're probably about the same size. So, the question is, do they have the same kind of active fraction? Are they putting off the same amount of dust given the same heat? And before I tell you the answer to this question, I'll mention I've had a summer student this summer working with me on this and related projects, Erilyn Flynn of the College of Worcester. She's looking for graduate school leads. So if you have any ideas for someone who's really excellent, really hardworking, and really intelligent, and is interested in this kind of stuff, please reach out to me. The answer to the question is no. Given the same likely size, the same orbits, all that stuff, their AF-rho values are about a factor of 15 different. We were kind of shocked about this at first, but we think we've kind of figured out what's going on. It's not due to sort of short-term variability that might not be well sampled by certain kinds of LSST cadences or other survey cadences. We think, if you can rule out, the recent orbit, the modern sizes, it has to be the more long-term orbital evolution. In some sense, the photometry, our actual assessment of their brightness, is able to help us pick out what kinds of previous dynamical pathways they've been in a way that might actually explain their differences. And there is evidence here that V6, the much dimmer of the two objects, was previously in a much warmer Centaur-like orbit prior to its insertion into a co-orbital state back a couple of years ago. You can see the images on the right. LD2 is 3 magnitudes brighter than V6 on the left. They just, even if they're in the same orbit, they're the same size, they're just not active in the same way, and you can tell. There is some uncertainty on those sizes, which might account for some of this factor of 15, but we have had a Hubble proposal accepted to check, and I think that's going to help. One thing that's we got interested in looking at, sort of for the same reason, is just looking at how active comets are at this distance. There haven't been a lot of surveys done. LSST will kind of sweep up on this. Part of it's that you need a lot of time on a 4-meter to go out and measure the value for one comet. And as a result, this is sort of a subsample of some of the surveys that have been done in this region. We need, Rubin to do better in this area, but these two objects sort of blanket sort of bookend the kind of activity strengths we can see in this region. And for context, LD2 is about as active as the largest Shoemaker-Levy 9 fragments, which were really quite active, losing lots and lots of mass, especially for their small sizes. And V6 is about as active as a Jupiter family comet at aphelion. In some sense, they kind of fit your idea of the two populations we'd expect to be entering this region. We can't do it with orbits alone, we can't do it with photometry alone, but maybe both. So I'll speed through these last few slides because I think I have a minute to go. We expect that there's probably something like 10 to 20 more co-orbitals that Rubin is going to be able to discover. Estimating the total yield on things like temporary captured objects, which would then lead to impactors, is a little bit tougher. And some objects that are in rapidly evolving orbits might need more frequent astrometric follow-up. We're going to be measuring lots of AF-rho values just in terms of the magnitudes of comets measured in these 4 to 5 AU range where water ice starts to sublimate. And I think that's going to really kind of change our ability to interpret even limited data sets on these objects. We're building some dynamical tools in this area. I'd be happy to talk about that offline. And here's my takeaway slide. I think the point is that, at present, we only know of a handful of these objects. And I think we can think of all the different reasons why they're interesting, but it's going to be getting them to be a bigger population that's going to let us actually take this into a much more sort of fully fleshed out field. And I think this is going to be really interesting in the next couple of years. So I'll say thanks.
Thank you very much. Questions?
Andy Rifkin, APL. So this all sounds really interesting. I guess I wonder if you have any idea how easy it will be to distinguish between near Jupiter comets, particularly ones that might have been temporarily captured, and irregular satellites, which presumably are also, I assume, well, we don't know the science frequencies distribution, but there might be a zillion more to find. Do you have any thoughts about, especially if the cadence isn't going to be optimized for doing this, whether things are going to be in this kind of liminal state for a while?
I think you've diagnosed a real problem. I think there are going to be objects which are going to be challenging to sort out which category to really put them in. One of the reasons that we expect that you should be able to sort this kind of stuff out is that, for instance, at least from distinguishing, for instance, like centaurs versus JFCs, the JFCs approach Jupiter at aphelion. There's a much lower relative velocity than compared to the centaurs, which are approaching at perihelion. You know, those two might differentially populate, for instance, the temporary captures versus the co-orbital states differently. And then, you know, we're going to be able to study, you know, once we have more objects, sort of the full range of dynamic behaviors that you can expect from these sort of temporary objects that are stuck around Jupiter from the more long-term sort of irregular satellites. We hope those are distinguishable, but I wouldn't be surprised if there are objects that are sort of permanently a little hard to understand.
Yeah, hi, Derek. Colin Snodgrass here. I was wondering, do you have any spectroscopic information about these things? Do you know if you've got differences of activity level, but do you know if there's any differences in what gases and things you're seeing?
Yeah, there's some evidence. So we have spectroscopic data on the brighter of these two objects, and we're working on the less bright at present. You know, it's at 22 magnitude, so it's a little tough to figure out the right strategy. But one thing that I think is probably the case that helps explain why LD2 is so bright is it probably has a really significant icy grain fraction. You know, it hasn't lost a lot of the icy grains that might have been in its outer regolith that might be quick to sublimate once you spend some time in the inner solar system. So even with relatively low SNR spectra, you can pick out its water ice bands. That might be something that can be done with, you know, even just near infrared photometry on these dimmer objects that might let us make that kind of a standard way that we characterize them. But we're still sort of working out the exact right ways to do this, especially as the population grows.
This is just a short comment. On Monday, we'll make a presentation about a new survey of comets in temperate satellite capture around Jupiter that with a telescope in the last perihelion passage of Jupiter last year. And I will discuss this, this possibility to how to distinguish then in the velocity space phase.
Awesome. I look forward to it.
Great, thank you. Let's thank our speaker again and we'll move forward.
Okay, next up, we have Saeed Hamidouche, who will be speaking about the dust and gas production rates, monitoring of long period comets and dynamically new comets with TRAPPIST telescopes.
Yes. So good afternoon, everyone. My name is Said. I'm a PhD student at the Cadet University in Morocco and also at the University of Liège in Belgium. I'm here to talk about my work. As an example, I want to talk about the dust and the gas production rate monitoring of long period comets and the dynamically new comets with TRAPPIST telescopes. So as a first small introduction, what is a comet? So comet is a body made of rock and ice, typically a few kilometers in diameter, which orbit in the sun. So this is a real picture of comet 67P captured by the Rosetta mission, and this is how it looks like compared to Los Angeles City, just to get an idea about the size of comets. So the origin of comets, we have two dynamical type: the short period comet with a periodic comets less than 200 years, and the long period comet located at the Oort cloud with the orbital period longer than 200 years. So why do we study comets? So comets are interesting because they retain a physical and chemical record of the primordial solar nebula and the process involved in the formation of the planetary systems. So the atmosphere of comets, or the coma. So when the comets get heated with the sunlight, the species get evaporized, and we can observe them with in photometry or in spectroscopy. So this is an example of different species that we can find in the comet's coma. So for the photometric part of this work, I use the TRAPPIST telescopes, which are two 60-centimeter robotic telescopes. TRAPPIST South located in La Silla Observatory in Chile, and TRAPPIST North located at the Ukimdir Observatory in Morocco. So for the equipment of TRAPPIST telescopes, we have the NASA HP narrowband filters. We have the gas filters, like you can see in red, OH, NH, CN, C2, and C3, and also the dust continuum filters. You see, and there in green, UC, BC, GC, and RC. In addition to those filters, we have the standard Johnson cosinus filter, BVR and I. So this is a TRAPPIST observation eclipse for the comets that I share in this work. I present here 6 different comets. Dynamically new and long period comets, and the plot shows the heliocentric distance range for comets observed in this work. The star present the perihelion, and I showed here the observation before and after perihelion. So this is an example of image of comet 20F3 Neowise, captured by TRAPPIST North at the Ukimdir Observatory. We can see here at the top images with narrowband filters, OH, NH, CN, C2, and C3, and also images with the dust continuum filters, like as an example, BC, GC, and RC. And also at the bottom, some images with the broad band filters, BVR and I. So this is this plot shows the light curve of all of the comets, like the magnitude evolution, and the 4 filters, BVR and I, compared to GPL ephemeris, and also fitted with the magnitude formula at the bottom. And here, those plots show the IFO parameter, the proxy of the dust production for different filters, BC, GC, RC, and also R and I for all of those comets. And to calculate the prediction rate, I used the hazard model. And as you can see here, the hazard model assumption, there are a lot of approximations, like the comet has a spherical nucleus and so on. And this plot shows the fit that we use with the hazard model, like the red dashed line, the observed profile, and the continuum profile. And the red line is the profile after the dust abstraction, and after fitted by the hazard model in the green line. And here those are the gas production rates evolution for all of those comets. As we can see, for example, for comet 12K1, the evolution of OH, NH, CN, and also C3. And for the spectroscopic part of this work, I work with data from the Indian telescopes, from the 1.2 meter Mount Abu infrared observatory and 2 meter Himalayan Chandra telescopes, thanks to the Indian colleagues that they provide us with data for those comets. I have simultaneous observation with the photometry and also spectroscopy from these telescopes. This is just an example of long slit images that I work on those data. This is an example of comet 17 T2 Pan-STARRS in January 13 in the Mount Abu Observatory in India. And this is an example of the optical spectrum of some comets. Like as you can see here, clearly detection of daughter molecules like CN, C2, C3, and also in H2 for different comets and different dates. And that's it for me. So work still in progress. I need now to work carefully to compare between photometric data and spectroscopic data, and also to compare between those two groups of comets, and especially in some specific heliocentric distance. So that's it. Thank you very much for your listening.
Thank you very much. Do we have any questions?
How far in advance do you need to schedule time? So if you know a comet is coming, you know, a year from now or 2 years from now, could you do that, or do you have to kind of do it? Well, I guess that's the question. How far in advance do you schedule this? If a comet just shows up, do you get the chance to kind of get on these telescopes?
Yeah. So since the detection and the confirmation of comets, we can start monitoring. But with TRAPPIST telescope, we have a limit of 18 magnitude, so we can do more than this to start monitoring a comet further away, I mean, into inner solar system.
Any other questions? Okay, thank you again, and we'll move on to the next talk.
Okay, for the final scheduled talk before the wrap-up, we have photometric properties of active asteroid 248370, 2005 QN173, from observations in Slovakia and Tajikistan. Talk to be given by Gulchera Kokryrova.
Thank you very much. Good afternoon, dear colleagues. Today we present a study of active asteroid which belongs to recently discovered new group of small bodies in the solar system. These objects show signs of activity in the form of tail and coma, characteristics for comets, but they have dynamic properties characteristic of asteroids, as a result of which they were called active asteroids. Oops. Okay. Asteroid QN was discovered in 2005 and is located in the outer region of main asteroid belt. On July 7, 2021, activity in the asteroid in the form of long dust tail was detected by Atlas program's Survey telescope, and then it was confirmed by observations of Lowell Discovery telescope. Because of the sudden activity, object along the asteroid designation began to be called Comet 433P. Initially, it was believed that cometary activity at the asteroid first appeared in June-July 2021. However, later, asteroid's activity was revealed from archival images from July. Main orbital parameters of asteroid are given in these tables. According to Tisserand parameter, asteroid moves along a typical asteroid orbit. This fact and the location of the asteroid in the main asteroidal belt, as was commonly believed until recently, clearly imply that the object is a primordial asteroid. But this asteroid moves in asteroid orbit and shows signs of cometary activity, as a result of which it was classified as active asteroid group. This group also includes main belt comets. Observations, quasi-synchronous observations of asteroid were carried out in July-August 2021 in Skalnata Pleso Observatory in Slovakia and Sangloh Observatory in Tajikistan. A summary of observations in 2021 and the results of photometric measurements are given in table from the left. Light cover of our observations shows variations in asteroids brightness over 3 nights in July, and we can clearly see 4 or 5 peaks with small amplitudes. Observations in August also revealed the presence of several small peaks, but on August 6, there is a sharp increase in brightness with amplitude of 1 magnitude. Small term changes in brightness may result from changes in albedo and the presence of large structure on the surface of asteroids. The change in brightness in August 6 may be associated with a recent one-time new local dust emission. Apparent brightness was converted to absolute using empirical model of Pentila and relation of Powell, which takes into account the change of asteroids brightness in the broad range of angle phases. And according to our measurements, absolute brightness of asteroid in air band range from 14.6 to 14.9 and show a slight tendency to decreasing. We also assessed the level of dust activity of asteroid using AF row parameter. As can be seen from this table. We can conclude that these values of dust productivity parameter show a very low level of object activity, and such values are close to those for Jupiter family comets at large heliocentric distances. Magnitudes of QN asteroid were measured at the same period by using Sloan system by Xi et al. To compare our data with these results, we transformed Sloan absolute magnitudes into corresponding values in Jones system using transition formulas from Georgia. And some results are presented in this table. As seen, results obtained are at the same dates, but in different observations with different telescopes and filter systems agree well with each other within the measurements errors. So, and dust productivity parameters also given in this table for 2 different sets of observations are in good agreement. Dust activity of asteroid in relation to coma formation is characterized by a rather low level. In addition, it must be taken into account that asteroid has already passed perihelion, and if his activity is associated with sublimation process on the surface, then this distance of the asteroid from Sun should undoubtedly affect the level of activity. So, briefly, our conclusions. I may finish my presentation. Thank you very much for your attention.
Thank you very much. Questions?
Are there other active asteroids that you are planning to study as well as this one?
Yes, we already have a lot of papers devoted to investigation of active asteroids. And for example, one object which was presented here, C2019 LD2, also was studied by us, and our papers were published. And we intend to continue our observations and research with some directions.
I'm curious about why you compare the activity of this object to Jupiter family comets instead of comparing to other active asteroids. At this case, we compare our observations with another set of observations. But basically, when we study such objects, we systematically compare our results and results for different asteroids between each other in order to make a conclusion. First, what is the reason of such activity? And second, to which kind of objects we can relate this or another asteroid active object, maybe to Centaur group, or maybe dual state objects, and so on.
Okay, I just had one question/comment. So I've collaborated with you to do a stellar occultation by Triton from the observatory in Tajikistan. I'm wondering what other, so you're clearly doing asteroid observing as well. Are there other objects that you have active programs to observe, or things like occultations that you're doing?
Yeah, you write us about these Triton occultations, and we perform these observations and submitted your results. Yes. Okay?
Yes. So you're doing things other than asteroids.
We're ready to continue such collaboration. And if you can saw that sun-glow observations, our telescope is very good, very quality,
yes,
good
indeed.
quality. So we're ready.
Thank you.
Thank you for you.
We'll thank our speaker again.
Okay, for the wrap up of this focus meeting, we have the organizers thereof, Nick Erasmus and Amanda Sikafus, who also deserve a round of applause themselves.
Thank you very much. We opted to allot the last 10 minutes just to have a quick wrap up. I know you're all eager to get out of here. We're not actually going to take that whole time. But I thought we've got a few announcements and just a few comments. I thought just to summarize what we've heard over this focus meeting, I think it's been a really wonderful meeting where we really appreciate the involvement of all the speakers, the good questions, and we hope that for the rest of the IAU meeting while you're here, we can continue to build collaborations. Some of the takeaways, we've heard a lot about LSST and what we're looking to expect, and it's coming soon. We heard today that in another few months, we should be expecting to get alerts about asteroids and objects. And of course, we've heard about the brokers, how we're going to get these alerts. We've heard about data pipelines and reductions, how the MPC is going to deal with this. We've heard about different facilities, both 8 to 10 meter class type facilities, and why those would be valuable small telescopes, about the variety of the facilities we have all over the world. We've heard about ones in Africa and Southeastern Europe and Central Europe, Serbia, Ukraine, ESO, what all these different places are doing to prepare. We've got some missions, Spherex, NEOMIR, the Korean NSOS, lots of variety that we've been talking about. And then of course, how we plan to characterize things. We've talked about spectra and photometry and rotational properties, sizes, activity, radar. There's an awful lot going on in this session. And I think this is really good because I feel like the only way we're going to be able to take advantage of this is to coordinate well. And I just wanted to mention a couple of things that stood out for me today. One was a comment that the advent of LSST and all of these new discoveries is going to change the way we do science, because we're all going to be swamped with the amounts of big data that we're seeing. And that's something that hadn't really sunk in for me yet. And then Marco made an interesting comment, right? That the rapid follow-up observations that we've been discussing, some of those may be needed immediately for things that won't even have an impact for another dozen years or more. So being cognizant that it's not always about what we can observe right now because of right now, but looking into the future as well. And then being able to combine different types of data sets is really important. So we heard today about combining, say, sparse and dense light curve data to really leverage that. So does anyone want to say anything else of anything that stood out to wrap up the meeting? Stop hitting the table now. All right. Well,
Anyone online want to say anything? Or type something?
So nothing else? Okay, so then we just wanted to remind everyone that there's going to be a proceedings for this conference. Our focus meeting gets allocated 50 pages, so we unfortunately can't accommodate everyone because they don't want just little abstracts, 50 abstracts. They want sort of at least 1 or 2 pages. So I've had responses from about a handful of people that want to contribute, but we can probably accommodate 1 or 2 more, maybe more, up to 10 or so. So if you're interested in the work that you've presented in the conference to contribute to that proceeding, please let me know. But at least, you're going to have to at least commit to 2 or 3 pages. Then something interesting that I actually only found out a few months ago was that PDC, the Planetary Defense Conference, is going to be in South Africa in May next year. So maybe I'll see some of you guys next year sometime as well. Oh, and if a bunch of people are coming, we might think of sort of a offshoot one-day workshop. So just if you have an idea like that, get in contact with me. Maybe we can do something like that. We can wait until the end. Oh, do you want to say?
Thank people at the end.
Okay. Before Amanda, thanks everyone. The weather is going to be awful this weekend, so I don't know how much hiking is going to take place or some of the other activities. So I'm thinking of maybe organizing a wine tasting event. So it'll be at your own cost and at your own effort to get there, but I'll pick a place that's sort of within Uber taxi distance. So I'll leave my computer out there. You can put your email address on there or just email me directly. It's probably going to be tricky if we're like 30 or 40 people. So if you're really very keen and interested to go, I'm thinking maybe Saturday. So I'm probably going to have to reserve a place sometime tomorrow. So I will check my inbox and also check the names that you give me now, and I will make a booking for however many people I have. Yeah, so the idea would be to meet at a wine farm somewhere, do a wine tasting, and let's see where the day takes us. Maybe we have lunch there or something. At your own cost and at your own effort to get there, of course.
And then finally, we did just want to thank everyone that was involved. It's published online, but especially our SOC, it wasn't just Nick and me. We have Antonella Barucci, who's here, Irina Belskaya, Julia De Leon, Estela Fernandez Venezuela, she's here somewhere, Alan Fitzsimmons, Hijay Lee is also here, Marco Michelli is here, and David Trilling. So we really appreciate everyone's help, and thank you all. Go well.
And then just also the chairs. Thank you very much for the chairs.
Yes, the session chairs. Okay. Yes. Sorry about that. Yeah, that way I didn't have to.
Hi. Hey, sorry to bother you, but I wrote to Kuzani and I didn't get any reply and I'm not on the program. Am I supposed to go or not? No, not the one that Cyril showed you. So I'm not sure what am I supposed to be doing. I mean, I'm happy to go, but anyway, just to be sure.
I thought Cruzani could be a little bit more difficult to communicate, but she replies to WhatsApp. So.
Oh, okay, yeah, yeah, that was my other question. If you had any other way to like.
I'm gonna ask her right now.
Yeah.
Okay, then I send you a...
You mentioned Lorena. Is she here or not? She's just on the SSA. Yeah. God, I think she was on Is she She must have left. We did have a talk from Ukraine over Christmas, though. I don't know if you saw that one. Where they showed the train that had been cleared. But that must have been early in time. His last name is Julia. I don't know him, but yeah, it was like right in the fresh barbarians. That's also good. So I'll just check it. I'll see you tomorrow.
Do I sign up?
Yes, against it. Yes. Because it sounds like I guess so. Yeah.
It's gonna be
Sorry, hi. I was just wondering what happened with the telescope in the end. It's like deep mics, like is there people who is...
Well, it's here, but I don't know how. I mean, for the Celestia event, I don't know whether they're going to be able to do that.
Because we were thinking he may stay, so that would be a possibility to go with them. But
it's at the University of the Western Cape, with the Department of Physics and Astronomy. Yeah, we can give you the contact at UWC of who to meet up with. It's here. I mean, Mike left them the camera. I don't know that he said they